progress.
Assalamualaikum warahmatullahi wabarakatuh. A very good morning to all of you ladies and gentlemen and
welcome to the International Conference on Science and Applied Science ICSAS 2023. It is an honor for us to welcome you all of you here solo in this conference today. On behalf to the organizing committee, I am Iqbal and my partner also,
Rizky Amelia.
We are from Physics Graduate Program Universitas Sebelas Maret. Would like to extend our gratitude and also great appreciation for your existence here.
Ladies and gentlemen, on this beautiful occasion, please allow me to greet the conference chair and also be invited speaker of ICSAS 2023. We can give a round of applause, ladies and gentlemen, to the Honorable Professor Kuncoro as Vice Rector for Innovation Research Affairs Universitas Sebelas Maret. Good morning, Prof.
Dr. Harjana S. Dean of Faculty of Mathematics and Natural Sciences, Universitas Sebelas Maret as well.
Prof. Fenty Suryanti as Vice Dean for Academic Research and Student Affairs.
Dr. Fahru Nur Rashid as Vice Dean for Planning, Partnership, Business and also Information Affairs.
Dr. Desi Sucihandayani as Vice Dean for Human Resource, Finance and Logistic Affairs.
Professor Chari as the Head of the Physics Doctoral Program, Faculty of Mathematics and Natural Sciences, Universitas Sebelas Maret.
Professor Budi Purnama as the Head of the Physics Master Program, Faculty of Mathematics and Natural Science, Universitas Sebelas Maret.
Professor Agus Suprianto as the Head of Physics Undergraduate Program, Faculty of Mathematics and Natural Sciences, Universitas Sebelas Maret. And also the Honorable our keynote speakers today. Professor Ariando from National University of Singapore,
Professor Muhammad Aziz from the University of Tokyo, Japan,
Professor Ramesh Kashi from University Malaya, Malaysia,
Professor Agus Supriyanto from Universitas 11 Maret, Indonesia. Also, a warm greeting to our moderator for today's conference, Dr. Ahmad Marzuki and Prof. Nuryani.
We also kindly enjoy this conference today as we are going to have a great discussion in the ICSAS 2023. Which is organized by the P6 Department, Graduate Program Faculty of Mathematics and Natural Sciences, Universitas 11 Maret.
Ladies and gentlemen, talking about the aim of ICSAS 2023 are to bring together scholars, leading researchers, and experts from diverse backgrounds and application areas in science. Special emphasis is placed on promoting interaction between the science theoretical, experimental, educational science, and engineering.
So that here a high-level exchange in new and also an emerging area within mathematics, chemistry, physics, biology, applied mathematics, and also all areas of sciences in achieved. So that's why here we are so happy today to welcome you to this discussion of the ICSAS 2023. And we hope this conference to be fruitful and also engaging for all of you.
Ladies and gentlemen, to start this great occasion, we invite each other and everyone to you to sing the Indonesian national anthem, Indonesia Raya. Audience, if possible, please be raised or please be in a proper position.
Indonesia, tanah airku, tanah tumpah darahku. Di sanalah aku berdiri, jadi pandu hidupku. Indonesia, kebangsaanku, bangsa dan tanah airku. Marilah kita bersatu, Indonesia bersatu. Hiduplah tanahku, hiduplah negeriku, bangsaku, rakyatku semuanya. Bangunlah jiwanya, bangunlah badannya untuk Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya.
Ladies and gentlemen, please be seated.
Ladies and gentlemen, the next agenda we have distinguished guests. We are proud to present the Gambyong Pare Anom dance which will be performed by UKM UPKD FKIP UNS.
Gambyong Parenom is a traditional Javanese dance from Indonesia, characterized by graceful movement and intricate choreography. This dance is often performed by a group of female dancers and tells a story about love, courtship, and grace.
Also, the dancer wear the colorful traditional Javanese dress and use fans in their performance, adding an elegant and mesmerizing element to the dance. Gambyong Pare Anom is a beautiful and cultural expression of Japanese artistry. So enjoy this moment. you so much for the nice performance, and also everyone please give round of applause to UKM UPKDFK UNS. So ladies and gentlemen, before we go, we have a photo session for today. So for the commit, please to come forward. And also to invited speaker also, please come forward.
Ladies and gentlemen, to begin this agenda, I would like to give a chance to the committee chair for giving the deliver his speech. I kindly please Professor Budi Purnama as chairman of ICSAS 2023 to come on stage and to deliver his speech. Ladies and gentlemen, please give a round of applause to Professor Budi Purnama.
Assalamualaikum warahmatullahi wabarakatuh. Honorable Vice Rector for Academic and Student Affairs, Professor Kunchoro Diarjo, Honorable Dean of Faculty Maths and Natural Science Universitas Sebelas Maret, Dr. Harjana, Honorable Keynote Speaker of ICSAS 223, Professor Ayando. Good morning, Prof. Professor Ayes, Professor Rames and Professor Agus Supriyanto, and presenter ICSAS 223 and colleagues from Physics Department Sebelas Maret University. First of all, we would like to express our gratitude to Allah, who has given us health and opportunities so that we can meet in this ICSAS 223. And second, on behalf of the organizing committee, we are honored and delighted to welcome you to the International Conference on Science and Applied Science, ICSAS 223. This conference was the 8th conference which was organized by the Physics Department, Universitas Sebelas Maret. On this occasion, the ICSAS 223 was held hybrid conference on this day, where on parts face-to-face on-site conference in here and other via online Zoom meeting. The ICSAS 223, there are 6 parallel sessions and 4 keynote speakers. The keynote speaker as follows. First, the Professor Ariando from National University of Singapore. And second, Professor Muhammad Aziz from Tokyo University, Japan. Third, Professor Ramesh Kasi from University of Malaya, Malaysia. And Professor Agus Supriyanto from Universitas Sebelas Maret. Well, for the conference participant, there is 92 participants which was submitted abstract via the conference system. Then, after review process, the 56 papers will be presented to the 6 parallel sessions in this year. We deeply thank the authors for their enthusiastic and high-grade contribution. The ICSAS 223 would not be possible without the dedicated effort of many people who have worked with us in planning and organizing the program. We are grateful to volunteers who contributed the various processes that make up the conference, and it would not be possible for me to mention one by one in this short message. I hope that during this conference you find the conference fulfilling and enjoyable. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Professor Budi Purnama, as for the welcoming speech today.
Ladies and gentlemen, we are also pleased to invite the Vice Rector for Innovation and Research Affairs Universitas Sebelas Maret, Professor Kunchoro, to give an opening speech and to open the conference officially. Ladies and gentlemen, please give a round of applause to Professor Kunchoro.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Honorable the Dean of Mathematics and Natural Science, Faculty of Mathematics and Natural Science, Prof. Matya Harjana, PhD, and also all Vice Dean of the faculty. And also Honorable Professor Budi Purnama and Professor Chari as a conference chair. Honorable keynote speakers, Professor Muhammad Aziz from Tokyo University, Japan. Professor Ariando from National University, Singapore. Thank you for coming in our university, Prof. Ariando. Professor Ramesh Kasi from University Malaya, Malaysia, and Professor Agus Supriyanto from Sebelas Maret University, and honorable all speakers and all participants. On behalf of Sebelas Maret University, I am pleased to welcome you all to the 8th International Conference on Science and Applied Science, ICSAS 2023, organized by the Physics Department Graduate Program Sebelas Maret University. First, I would like to congratulate the organizing committee for successfully holding this international conference. And I hope it should be more lively and have more participants compared to the previous conference in 2022 because the COVID pandemic has passed now. In this area of rapid development of science and technology, we have to promote interaction between the science, theoretical, experimental, and educational sciences and engineering so that a high level of exchange in new and emerging areas within mathematics, chemistry, physics, and biology, all areas at science and applied mathematics and science, I hope can be applied. Therefore, this conference is very appropriate to the current situation around the world, including in Indonesia. Here, I hope all of you, scholars, leading researchers, practitioners, and experts from diverse background and application areas in science can engage in a meaningful discussion on the critical issues in physics, biology, mathematics, chemistry, education, engineering, and many collective contributions to find new innovation of needed new things. At this moment, I hope you all can collaborate in research and other activities. I hope please share your research findings, experiences, and the best practices in various fields, including physics, biology, mathematics, chemistry, education, engineering, and other related disciplines. It can be concluded that interdisciplinary dialogue and collaboration are just right to develop innovative science and technology for manufacturing a sustainable, innovative product in the future. Once again, I would like to welcome you all to this conference while expressing my heartfelt appreciation to the organizing committee, sponsor, our esteemed keynote speakers, and all participants. You can do walk here, and after this conference, you can do shopping in Solo City. So workshop is a right statement here. Yeah. Okay, I hope you all are in good health today. Thank you very much for your attention. By saying Bismillahirrahmanirrahim, this conference was officially open. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Kunchoro, for opening ICSAS 2023 officially.
Ladies and gentlemen, so we have here agenda is giving merchandise for Professor Kunchoro and also Dr. Harjana. Please come forward to give merchandise for Professor Ariando and also Professor Agus Supriyanto. Also, please come forward to the stage.
Okay, thank you very much. Next, we have a photo session for the participant in the Zoom meeting. So, for the participant in the Zoom meeting, please turn on your camera and smiling. For the slide one, we will take the photo. 1, 2, 3. Okay. Again. 1, 2, 3. Okay, next slide. 1, 2, 3. Okay, and the next slide. 1, 2, and 3. Okay, thank you for the participant in the Zoom meetings for take a photo session. Ladies and gentlemen, we are going to move on the next agenda. We will begin the first session on the plenary lecture with Professor Ariando and Professor Muhammad Aziz.
And also to make this session run smoothly, I would like to introduce our guest moderator for this conference today. We have here Dr. Ahmad Murzaki. Mohon maaf, Dr. Ahmad Marzuki. He was graduated from Physics undergraduate program, Universitas Diponegoro, and also Physics doctoral program, University of Leeds, England. And currently he is occupied here as a lecturer in Department of Physics, Universitas Sebelas Maret. And his research here is focusing on optoelectronics, laser, and also energy, and also he is acting on Center for Disaster Studies. Ladies and gentlemen, I present you Dr. Ahmad Marzuki, please, and the time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Okay, dear Prof. Kunchoro, the Vice Rector of Sebelas Maret University, and also Dr. Harjana, the Dean of Faculty of Mathematics, Sebelas Maret University, and ladies and gentlemen, who join this conference online and offline, yeah. Okay, have joined with us today this morning to guest honor, yeah, that will give lecture talks for us in this conference. The first is Professor Ariando, and the second one is Dr. Muhammad Aziz. Prof. Ariando will deliver his talks on quantum material by design for sustainable future. This is the material that we use to build modern material that we need today. And also Dr. Muhammad Aziz, yeah, who will deliver talks on advanced adoption of digital twin technology in clean energy system toward carbon neutral society. Let's start with the first talks that will be delivered by Professor Ariando. Please come on stage, Prof. Ariando, and please welcome to Prof. Ariando. Yeah, please come. Okay, Prof. Ariando will deliver his talk for 30 minutes, and after that will be time for Dr. Muhammad Aziz, who also deliver his talk for 30 minutes, but Dr. Muhammad Aziz will deliver his talks via Zoom, yeah, via Zoom. So, the time that we give to Prof. Ariando for discussion is just after Prof. Ariando deliver his talks. Before Prof. Ariando deliver his talks, let me introduce him first. Okay, ya. Okay. Prof. Ariando is currently a full professor and deputy head of research and graduate studies of Department of Physics at National University of Singapore. He received PhD in physics from University of Twente, Netherlands in 2005 on superconductivity in joint work with IBM TG Watson Research Center. He then took a postdoctoral position under the Dutch Nanoscience Research Networks and joined the National University of Singapore as faculty member in 2008. He holds a number of patents and has authorized over 200 referred articles in leading journals with more than 7,800 citations, and his age index is 46, with over 100 invitations to speak at international meetings. He was the deputy of director of NUS, National Nanoscience and Nanotechnology Initiative, and has been recognized with Omicron Gold Medal by Institute of Physics Singapore, Young Investigator Award, Dean Chair, Professor, Outstanding Researcher Award, and Faculty Award for Mentorship Excellence, Faculty of Science, NUS. Next, visiting investigator at LNCMI, CNRS, France, and the 2023 Japanese Society for Applied Physics, best review paper, Japan. So it is very, very important for us. It is very interesting. He is very, very brilliant scholar, I think. Yeah. And let's start with his talks. So, Professor Adriano, stage is now yours. You have 30 minutes, Prof, and followed by discussion.
Jalan aja bisa ya di sini. Enggak usah. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. First of all, maybe it's too many names to thanks, but I'll just thanks everyone for having me here and for all of the hospitality. Okay. Well, it's always a bit challenging to talk to a broader audience, and especially even for physicists, right? Seeing quantum is always kind of scary. So, but don't worry, I'm not going to talk too much on this quantum aspect. What I want to try to highlight today is a future of the quantum, so-called quantum materials, to help us, you know, to remain possible to expand in terms of the technology. Right, but before going to the topic of today, let me also try to invite especially students from UNS to consider opportunities at National University of Singapore. Oops. Right, so why NUS and why physics? So, well, ranking is always something that maybe people are looking at, right? And but not only that, life and work balance in Singapore, I think, is quite good. You can also have a very, very cheap food. Okay? So living cost is not that high as people think it's used to. And yeah, it's very close to Indonesia, right? So in physics and US, we also have a different degree levels. So we have a bachelor degree, like what you have here. We also recently opened a master degree. We did not have master degree, used to not have a master degree, so bachelor degree can directly join PhD. But in the last 2 years, to bridge between, in particular students who are probably not really interested in doing PhD, but still want to do a bit more advanced study and then move to the industry. So this kind, all people who probably did not really gain too much during the bachelor degree, but then still wants to do, PhD. So we try to provide this bridging by giving these two different types of master degree, Master of Science in Physics, as well as the Master of Science in Physics for Technology. Right? So this gives opportunity for people to advance their study, and if they want, they can move on to industry with probably a bit better positions, or if they want and they can come up with a very good result, so they can move on to the PhD. So here I showed one picture of a recent PhD candidate that joined my group, so Nurul. So she is a lecturer in University of Airlangga, and she basically also secured the LPDP scholarship. And then I tried to bring her. At the same time, at NUS, we also have the opportunity to give scholarships. So I also challenged her to apply for the PhD scholarship at NUS. So she also won it. So at the end, she chose actually there are two types of scholarships. So she chose the NUS scholarship and then declined the LPDP. So, well, now she just started in Jan this year. So yeah, so this is one example. For example, students from here, right? If you are interested, right? So please feel free to contact me. So the funding support is quite good for PhD. It's depending on before or after you pass the qualification exam. So you will get this kind of amount, around 3,000 to 4,000 Singapore dollar. So this is one thing. And of course, join us for this PhD degree, because not only in my group, as in charge of research and graduate studies, so I would like also to promote our faculty members. So we recently attracted quite a number of young stars from all around the world, right, from different fields. So you can see there are many different opportunities in terms of what kind of research that you can do in physics, right? So please take a look at this website. So there are many more people. So these are just the recent hires in the last 1 or 2 years, and as well as that link to my research webpage. So you can please try to look at it, and then if you are interested, please, or if you want to know more, please feel free to interact with me. Well, this is Singapore in picture, but a real photo. You can see quite an interesting place to live in, or to study at least. This is the National University of Singapore. The one is so-called University Town. So this is where students and lectures can happen at the same place. Right? So we have the so-called University Town as well, probably similar to this place. So everything can happen at one location. So lecturers, students, they live in the same building, the same locations. Below is the view of the National University of Singapore. So you can see a very green place to study. Right? Okay, don't want to spend too much time now. And there are two more. So these are two programs targeted to Southeast Asia researchers or faculty members. So for example, this is the so-called NUS Fellow programs. So you can see this is to try to bring young faculty members and researchers from Asian universities. So this is targeted to only people from the Asian country. You see, opportunity is very good here. So this is one example, Geo. So Geo also just won this so-called NUS Fellows. So she is now at ITB doing a PhD degree. So she can spend like 1 year in my group, in my research group. And she also, of course, is supported by financially, as you can see there, it's around 4,500, something like that. Okay, and it is also targeted to not only PhD, so master students who are doing really great as the opportunity to also apply for this so-called NUS Fellow Program. So the last one is the so-called postdoctoral fellowship, which much better support, of course, but this is only for PhD. So for example, our faculty members here who just finished PhD, for example, but would like to get more experience, so please welcome to contact me and try to secure the so-called postdoctoral fellowship. It's typically like 2 years program, so to do a research at NUS. Okay, so let me go now to the topic of the conference that I'm going to talk about today. I changed the title slightly from Quantum Materials by Design for Sustainable Future to the so-called Brain, Artificial Intelligence, and Quantum Materials. But basically it's the same. My focus is on quantum materials. I try to bring brain, artificial intelligence, and electronics as the motivations why this quantum materials is a promising future, okay? So the two pictures that you see here, this picture is basically a picture to demonstrate what quantum material is really. And what you see here is this vortices is basically something to do with magnetisms, but it does not appear in conventional materials like silicon and so on, right? So this is what quantum materials really, okay? Quantum material is materials that can have unique and unexpected properties governed by the quantum effects, okay? So these are examples of these emergent properties unexpectedly, right? And only happens when you have the so-called quantum materials. And this is something that we can hope that can be used to produce something which cannot be produced by conventional system any longer, right? Which is kind of limiting our capability to expand, for example, in terms of electronics, okay? So let me start with introductions a little bit on the brain, okay? I'm not the expert of the brain. So about learning, So we know that since we are born on this universe, so things that always happen is this learning process, okay? Everybody, until we, go back to our, nature, okay? But what I would like to point out here, when this learning is happening, something that happens is, that always happens, that the change in our brain, okay? For example, like today, hopefully by giving a speech here, so you learn something. So I'm sure at the end of this talk, or at least hopefully there will be a change in your brain as well, okay? So if there is no change, then there's something that you can question yourself, okay? So to be more specific, what kind of change? So there is this so-called physical change. Yeah, so brain become soft, hard, that kind of change. Right? There are many things involved in this learning process. So for example, neurons, like our transistors. So this is where the core is, okay? So there are, 100 billions of them, okay? 10 to 11 in our language. And this is connected among them, okay? And this is what we call the synapses. So there are, even more of the synapses. Okay, the synapses that change as we learn something. Okay, so it become maybe strengthened, weakened, elongated, and so on. Yeah. So our brain can also do calculations, a huge amount of calculations. So the so-called floating points, exaflops per second, 10 to the 15 of them happening, much more than what we used to have in our computer, for example. But what amazing is about this learning by our brain is this only involves this kind of mass, 1.5 kg things, right? 1.5 kg, but the capability that we have here, you can imagine. And the other one is the energy involved, right? 20 watts. So it's just, this is, if we used to have a bulb at our house, right? The, what is it called, with that filament? We used to have like 100 watt at least, right? To make it a bit more light, right? But our brain is only 20 watt. So the main thing is here that I'd like to point out is this learning involves the brain, materials, okay? So there is this process of so-called materials learning. You probably heard, if you talk about this brain, it's so-called plasticity. So this is the change in the materials, right? Well, just intermezzo, perhaps for this guy, slightly a bit more in terms of all the parameters that we see just now. Looking at him, reading these books. So this is one thing. So small mass, very, very low energy, okay? So this is our brain, right? So here I'd like to play a little bit of game to highlight another thing. So let's test our brain. So this is the number. So can somebody tell you what the product of this one? Quickly. Give 10 seconds. Somebody? Don't use calculator. We are checking our brain now. But Woody, how much? 1, 2, 3, 4, 5, 6, 7, 8. Still not come up with something yet? Okay, okay, then I move on to the next questions. So it looks like, oh, very good, okay, at least. Okay, so next question is, what did we see? Mr. Bill. Baby Bean, okay. Well, so here the point that I like to try to bring up is, so you see our brain is not so good in exact calculations, right? Very slow. But in, for example, looking at this picture just now, memorizing things, recognizing patterns, very, very good, right? So we can immediately link to something, we can remember it, and then we can, yeah. So this is something, yeah, so in terms of energy, it's very, very good, very, very low, okay, very efficient. It's not so good in trying to do exact calculations, but it's very good in, pattern recognitions and things like that, okay? So, well, of course, because of this, since, let's say, very, very old days, even thousands of BC, so we have tried to help our brain in doing calculation, for example. So we have all of these tools till this decades. Now we have this very powerful computer, right? So this is basically trying to help in trying to do these calculations. Well, this is our technology in comparison to the brain. And in the last 5 decades also, so not only a simple computing technology, this idea of the artificial intelligence, the idea of the machine learning, and the idea of the deep learning, so trying to engineer electronics to replicate the brain, right? But beyond that one, if it's just computing technology, we can only do this calculation. So that's what we have been doing in the last, this computer, all of them. But artificial intelligence come, beyond this, with the idea to be able to solve beyond just a simple calculation. So we can see with this AI, machine learning, so we are trying to, for example, also do this pattern recognition. So machine will try to, with just a simple programming, so then we let the machine to adapt, to learn, and then, so this is the, the idea of trying to also come up with something beyond what brain can do, okay? So just to put in perspective, so the supercomputer in the last latest technology, for example, if we look at that number there, so the volume is the area, so occupy 680 meters square. To achieve a similar kind of number of neurons that we have in our brain, 58 billion transistors, right? So this is the amount, and the amount of money that we need to spend, hundreds of $1,000,000, and especially the energy, look at the energy. 10 to 6, 7 decades in comparison to our brain, right? So 20 megawatt. And just to put that side by side, so you can see 20 watt versus 20 megawatt supercomputer. And we try to look, maybe it's not a fair comparison. People have been trying, scientists have been trying to, to do this kind of competitions between AI and human brain, right? So this is one of the latest, don't exactly remember, I think 2016. Probably before you also heard about chess competitions. In this case, it's the so-called Go competitions. So it's much more complex games in comparison to chess, involving much more complex patterns, I believe. And you see, there were 6 games, I think, between this AI and Lee Sedol from Korea. And from among these 6, Lee Sedol only won 1 game. Of course, it's not a fair comparison. You can see power that we use for this player and the number of power that is being used for, for the AI, okay? Just to put it in perspective. All right, so the AI itself is possible, become even more possible nowadays is because of 2 things. So first is this supercomputer, so we have a very powerful computer. So computing power allows us to do this AI because it needs a powerful computer. But the second thing that you also see nowadays is this cloud computing, okay, big data. So to be able to really make progress with this AI, we have to have this big data, okay? And this is another big problem for our sustainability, to even expand beyond what we have currently, right? High power consumptions, extremely high power consumptions, right? So it's not just this supercomputer. So this big data, you don't see it because it's always there in data center. So in data center, they have a big servers, and then networking. So this also consumes a lot of energy, okay? Just again to give a perspective, this one data center where we access data for this cloud, big data, so consume energy, in comparisons to our houses, 180,000 households. So that's what amount of energy consumed by this one data center. So why is it, okay, this is just to highlight, if we remain this way, so if we just do this conventional cloud computing with supercomputer, and then having all of our electronics accessing this cloud, So this is the amount of energy that is going to be consumed just by this one. So you can see the blue and the green one increase significantly, exponentially, right? So this is the network as well as the data center. And altogether, you can see by 2030, the amount of energy, our primary energy will be, 20% of them will be consumed just by this consumer electronics or IT. Right? So this is not sustainable. This is from all of our different energy consumption that we are thinking, it's 20%. So this is a huge one. So this have to be changed, okay? So why is it inefficient and high power consumption? Well, I can go deep into the electronics, but I don't see we have time to do that. But just to highlight in terms of computing, right? So we have these two things: architecture, which make it inefficient, as well as the materials technology that we have will not allow us to overcome this architecture. So we have to come up with something new in terms of the material systems to be able to implement a new type of architecture. So in this old architecture that we have, the so-called von Neumann architecture, so the memory and the logic, they are not at the same place. There is always information transfer between them, okay? And this is simply because we don't have a system where we can build, for example, at this time, where we can have memory and, for example, logic at the same location, okay? So sequential operations that we have in our current electronics, right? So this is the architecture that we need to try to overcome to be able to be more efficient in terms of the energy. Well, there have been many different proposals in terms of how we can come up with something new. So we have this so-called new architecture, neuromorphic. So brain-like electronics, trying to build a technology or architecture where we replicate our brain. Qubits, quantum technology, this also giving us a much more computing power, okay, with less energy. And another route is trying to do invent so-called new materials. In this particular case, it's quantum materials, okay? So this is really the core of my research. So trying to come up with materials, quantum materials, with new properties, but by design. What I mean by design is something does not exist in nature, okay? So we try to design ourselves new kind of materials, and then hopefully that will be able to produce new properties that can be useful for our future technologies. All right, so I'll just give, so this now come a bit too deep to the science part of the talk, maybe just like 5 seconds. So I summarize the quantum materials routes that I'm trying to do in my lab. So something to do with so-called superconductivity. And as you know, superconductivity is this is one example of quantum materials, clear quantum material. So a quantum effect produces the so-called electricity, materials that conduct electricity without resistance. Clearly, in terms of energy, this is a very efficient, right? Because there is no heat generated, and there is no resistance. We also try to produce the so-called magnetisms, but with a texture which is unconventional and protected from the environment. So if you think about hard disk, for example, hard disk is based on magnetic materials, but it can be, for example, easily destroyed if you put close to magnet, right? But if you use magnetic materials, in this case, the quantum effect that produces the so-called topological spin textures, so this new spin arrangement, so if we can implement it into our hard disk, can be protected from the ambient, okay? And also in terms of the switching and the propagations of this magnetic element can be very efficient because of these protections, okay? And 2D materials is another very hot research nowadays. So you can also play with these 2D materials, which used to be considered just very conventional materials, but if you can do this so-called by design, so you can create a new emergent properties using these 2D materials. Okay, by design, how do we do it in the lab? So this is just a cartoon, how this happens actually. So you can see before that we put one atom layer, okay, and then another layers to create a new kind of compound that can interact between the layer, which does not exist in nature, okay? And then we try to investigate these properties, right? And of course, you have to be able to predict a little bit in terms of what happens, you know, when these layers are formed, right? And then to expect to have these new properties. So this is the actual equipment that I have. So this is my lab, one of the room in my lab. Yeah, you can see the left picture from your side. The vacuum equipment with laser where we can create these new materials, right? And the right picture is something what happens inside of that vacuum chamber, okay? So you will create new quantum materials. So this is also something that we are heavily working on. What you see here is a two-dimensional carbon atoms and stacked with another 2D, just like probably people have heard about graphene, okay, just a two-dimensional carbon atom. But in this case, it's not just one layer of this carbon atom, but two of them. What we can do here is to try to create a new kind of interactions between these two layers by, by doing the rotations between the two, okay? And because of the so-called formation of this new kind of lattice, new properties can also emerge. For example, the clear example is the emergence of superconductivity in these carbon atoms, which is not there when you have just a single layer, but when you put two layers, but then you twist by 1.1 degree, so somehow this coupled system become superconductor, can conduct electricity without resistance, but of course, in this case, still at low temperature. We also play more on this aspect, for example, by coupling not just two layers, but 3 layers, as well as, for example, with using two different two-dimensional materials. In this case is carbon atoms, graphene, and hexagonal boron nitride, HBN. So if you couple these two, somehow you can also produce new kind of properties. So superconductivity itself is something that we are heavily working on. As you know, superconductivity is requires cooling system to be working. So what people are trying to have, of course, to produce superconductivity that work at even higher temperature than nowadays. And yeah, so this is also something that can be done through these quantum materials by design. Yeah, so you take potential materials and then you try to modify, but at atomic scales with very precise modifications. Yeah. yeah, just as an intermezzo, so this is probably a picture, video that you can also find on the internet. So how the superconductivity properties can be utilized. So I mentioned about the conducting electricity without resistance, but another properties is this perfect expulsions of the magnetic field from its entirety. So then you can imagine this to something that can be used for, technology as well, okay? For example, the magnetic levitation is something that has been discussed a lot in terms of the applications of this superconductivity. Probably I don't have much time. I think 5 minutes. Still 5 minutes, oh, okay. So let me just skip this one. So this is something that is much closer to real applications. So we have been working also on the so-called memristors. So this is in comparisons to our transistors, which is the 3-terminal device. So memristor is basically just a 2-terminal device, and the on and off state, or 1-0 state, is defined by the resistance state of the system, okay? And as you can see here, the main thing that you can see is the so-called energy involved in the writing and reading of this so-called, logics, okay? Like in our transistor, this typically involves energy for switching on and off of around 10 to the 12, 10 to minus 12 joule. But with these new molecular memristors, as you can see, it can go below 10 attojoule. So this is 10 to the minus 15 joule, okay? It's order of magnitudes lower in terms of the switching energy. So this is what I said about this new magnetic state. So I think Pak Budi is working on magnetisms. I think hopefully the students also working on magnetisms. So instead of just using conventional magnetic texture, for example, we know ferromagnetisms having spin pointing up, pointing along the same directions, or anti-ferromagnetic spin pointing along the opposite directions, a ferrimagnet and so on. But with this tuning of the quantum effect, so we can create a new kind of textures of this, not just pointing up or pointing down, but creating a so-called a new quasi-particles where the spin is kind of twist along in the space, okay? So in total, it doesn't have a net magnetic moment, so it's protected somehow from the effect of the external magnetic field, yeah? And this is a very hot research in terms of magnetisms nowadays. For example, IBM proposed to use this as the new technology for memory, yeah? All right, so I'll just skip this one. Yeah, probably I just skip this one. So let me just conclude at this point. So what I've been trying to show to you all is the future of the quantum materials. So by trying to exploit these unexpected unique properties, which we cannot find in conventional materials. So hopefully we can overcome some of the limitations of the current semiconductor technology that can be implemented in terms of the new device, even completely new applications. And then we can keep up with the demand in our life in terms of the technology. Okay, thank you very much.
Okay, thank you very much, Prof. Ariando. This very nice presentation indeed. Yeah, this Prof. Ariando have give talks on quantum material. Yeah, we know that quantum material is with quantum material we can make new material from quantum point of view. That from the structure of the quantum structure, we can tune the new properties. That's right, Prof. Yeah, Prof. Okay, ladies and gentlemen, we have about 10 minutes for question answer. So I will divide this question answer into two parts. The first is for everybody coming to this room and everybody who joined via Zoom. So I will open the two questions from everybody coming into this room. Please raise your hand, please. Okay, hang on. Another ones from right side. Okay, just short question.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Jenny. Thank you so much, Professor Ariando, to tell about the quantum. Before this, I always think that quantum is really complicated and confusing, but you explained with a good way. So, but in my mind, that left in my mind after you explaining everything about that, I just remember about the postdoc pamphlet. So actually, right now, I'm currently doing my PhD in Malaysia, and my focus in the SSC research. So, is there any requirement for me to go there? And also, how many journals they should publish in every year to achieve the KPIs? Thank you so much.
Okay, next one, please. Just mention your name. Okay.
Okay, thank you. My name is Hasif from Statistics Department, UNS. Yeah. I'm interested in machine learning because machine learning needs training data and testing data, and the challenge in machine learning is the quality of data. How to ensure that the quality and the data that we can train the data as well as that in order to the high accuracy in the machine learning algorithm. Thank you.
Okay. I think two is enough. Okay.
Right, so thank you for the questions. So regarding the postdoctoral fellowships, what is your field again?
Dye sensitized solar cell research.
Solar cell research,
Yes.
okay. Oh, it's always, so the one that I showed to you is so-called fellowships. So this comes with a title, with that title. So there are two types of, let's say there are two types of postdoctoral opportunities. One is just like traditional postdoctoral positions that you can find, for example, from particular research groups. So, for example, just let me try to explain. So you find, for example, a professor at the university, for example, at NUS.
Yeah, can I find from you?
Yeah, I mean, and then you are interested to join the group, then you can directly contact the professors and ask whether they have opportunities or not, right? So in this case, you will, if the professor agrees, and then looking at your profile, and then you join the group, and then basically the financial support will come from that professor, typically research grants. So usually you will start with 1 year, and a typical one will be 2 years or 3 years sometimes, even longer.
2 years contract.
2 years contract, yes. So this is the conventional way of, but this is the one that I showed just now, a so-called fellowship with a title. So you come as a postdoc, but you also gain this title that you can put on your CV because it's more prestigious. So you are competing with different applicants. You are competing with applicants from different fields, so not directly from the professors, right? So if you are selected, it means you are very high in terms of achievement. So yeah, you get this title, it's more prestigious, right? So this is the fellowship that I'm trying to show. In terms of, you asked about KPI, we don't have a strict in terms of what the KPI should be. So it depends on the research groups, right? But so KPI typically will relate to, yeah, it depends on the supervisor, because at the end of the day, the KPI will determine bonus. Yeah, so in terms of financial things, right? And this bonus is always determined by the PI, by the professor. So there is no standard in terms of, yeah. If your group has always been publishing very good journals regularly, so then people will, the PI will see that, yeah, you have to also produce similar kind of things. So that's the, I hope that answered the. Right, and then in machine learning, that's a very difficult question, something that I also don't know what, how to answer that precisely. Because it's something that always going to be improved as you collect, as you provide more and more and more data, right? So by time, then everything will become better and better. For example, you do machine learning, try to have the program to compare, for example, to know that this picture, for example, a picture of apple, and then the other one is a picture of frog, right? And then you keep providing the data and the data. At some point, of course, it will be very accurate for this machine learning to detect. And then when you put this similar to apple, then it will predict apple. Similar to frog, then it will predict frog. And then, but somehow now you start to put a pictures of elephant. And then the machine learning will start to, from the beginning again, right? So maybe it tries to predict first, or, I don't know, because elephant and frog is a bit too big in terms of the size difference. So maybe, I don't know what the machine learning going to say, but yeah. But then you need to fit the data again. You see, so it's difficult to say in terms of how to know the accuracy, you're saying about the accuracy, what kind of data. So the more data, it will be more accurate. So that's probably the easiest answers. Thank you.
Okay, thank you very much. These are two questions from all of you come to this conference room. Now is a question from everybody join from Zoom. Okay, committee, can you help me? Is there any question from there? From Zoom? Okay, thank you very much. Okay, I think there are no more questions. Okay. Okay, if there are no more questions, ladies and gentlemen, I want to make comments, a few comments. First is, I want to conclude that with quantum material, we can manipulate material that can result in new unexpected material. This also apply for all other physical properties. Is that right, Prof? Yeah. Not only magnetics, but also like optics and so. Right, Prof?
Yes, that's correct. So just to give one more example, for example, ferroelectricity. So this is something that is also useful in technology.
Yeah.
For memory, for example. with quantum materials, for example, you can try to have materials not just having that ferroelectricity, but also combinations of new optical properties,
Yeah, okay.
or combinations of other properties in the same materials.
Okay. Okay, thank you very much, and please give applause for Professor Adrianto. Thank you very much, Prof. Okay, so everybody, if you have any more questions, then just send to him. Yeah, you can check his email from his website, and I think Professor Adrianto will happy to give you a help. Okay, now we move to the second presentation. The second presentation will be delivered via Zoom, I think. Yeah, via Zoom. I want to say hello to Professor Ayis. Assalamualaikum, Professor Ayis.
Dr. Ahmad, thank you very much.
Okay. Okay, Prof. Before Professor Aziz will delivering his talks, I want to introduce him a bit. Professor Aziz is a lecturer on in physics from University of Tokyo, yeah, University, and he will give a talks on advanced adoption of digital twin technology in clean energy system toward carbon neutral society. Okay, Prof. Time is now yours, Prof. Prof. Ayis.
Thank you very much.
Okay.
Dr. Ahmad, so I would like to share my screen first before starting my talk today. So let me do. Oh, sorry. The previous slide from Professor Arianda still, I think it's still active now, so I cannot share my screen. Can maybe anybody can
Yes.
help me for this one?
Okay.
Okay, thank you. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, selamat pagi for all of you. I'm Aziz from Tokyo University, and today it's my great pleasure to be invited for delivering a talk today correlated with some real issues also correlated with maybe some artificial intelligence and also some how we can use also some digital twin technologies, because it is quite different also between the digital twin technology, simulation technology, artificial technologies. We use them together in our research, and also we are because our research are mainly correlated with any kind of energy system. So today I just would like to much focus on the talk for how actually we can utilize this kind of technologies, especially in the field of energy systems. And today I just would like to talk or mainly focus on the carbon neutral energy systems. So I'm Aziz from Tokyo University, and my humble appreciations to all of the participants and also to my gurus over years. So we have also my respected vice rectors, Professor Kunchoro and also Dr. Hajana, and also Professor Budi Purnama, and also Professor Chari, and also finally also my great respect also to my seniors and also my guru also, Professor Ariando from NUS. Okay, before starting my talk today, I think I just would like to introduce our labs in Tokyo University. And this is our, maybe you can also access our website in this address. Actually, you can jump up to our website here, and you can find some information correlated with our research and also publication members or etc. in our labs currently. And we are much more focusing on the energy systems. Maybe the levels are quite different with talks from Professor Ariando previously, but we are dealing with much more higher or bigger systems over years. So we have any kind of elemental technologies developments and also some work related with how far we can design, and also building any kind of scenarios correlated with the energy system in the futures. And now currently we have about 18 students in our lab, especially And that's also including 6 students for having any kind of course provisions programs, especially from China and also other universities. And usually they are staying in our lab for about minimally about 6 months. So in case that some of you may be having any kind of interest or having any kind of visit in our labs, for joining our labs, for whether for being any kind of regular students or maybe any kind of visiting students or maybe any kind of visiting researchers, we are actually also welcoming for all of you for joining us here. So this is correlated with research that we are now conducting in our lab. We are starting from any kind of building the scenarios in the energy systems. We are designing and also how far we can optimizing the energy system that we built. And in here we can see over years that we are dealing with any kind of fluctuating supply and also demand side of the energy system. And finally also how far we can have any kind of intelligent systems of the energy for bufferings and the fluctuations between the supply and also demand side of the energy systems. And also finally how far we can provide any kind of high quality of the energy to the consumer. And basically for this research also we are not only focusing on the steady state levels of the energy systems, but also correlated with any kind of dynamic system. So dynamic system means over years that we are dealing with the real life. We are dealing with any kind of big data correlated with supply sides and also demand sides of the energy. Especially like for the renewable energy, we are dealing also with 10 years data and also maybe more than that to achieve any kind of much more accurate predictions for the energy systems. And then also we are dealing with any kind of elemental technologies developments. So we have any kind of technologies to produce the hydrogens, but also to separate the CO2 simultaneously. So we have any kind of, like usually we call it as the chemical looping technology for having any kind of CO2-free hydrogen production systems. And then we are also dealing with any kind of hydrogen storage. Maybe it is maybe strongly correlated with any kind of physics. So we built any kind of new structures for the hydrogen storage containers over here. So we call it as the triply periodic minimal surfaces. And we are targeting for building any kind of building any kind of structures which has good or excellent strength and also hydrogen storage density, and also finally also excellent heat exchange inside the container. And also we are moving for also hydrogen utilizations. And for this one, I think this is much more correlated with any simulations and also how far we can build any kind of real-time predictions. And also finally, in case that we can realize this kind of system, finally, we would like to build any kind of digital systems for hydrogen combustion systems. And also we are also conducting any kind of research correlated with the energy storage, especially for the battery. We have 2 different research topics over years. The first one is for the redox flow battery. So we must focus on the iron-based redox flow battery. And also the second one is correlated with a solid-state battery. But we are much more focusing on the how far we can avoid any kind of crack in the solid-state battery. And also finally, also it's correlated much more with the higher utilizations of the energy storage, including also the electric vehicles. So for the introductions, also the backgrounds of my talk today. So I think sometimes also I use this kind of slide to explain how far we have any kind of big concern correlated with the energy and also our sustainability in the futures. So when we are talking about the energy systems, finally, we have these 3 different pillars which are really important, really crucial for our energy systems. The first one is correlated with the energy security. The second one is the energy equity. And finally, also the third one is environmental sustainability. For the energy security, I think there is any kind of big shift from moving from the conventional definition of the energy security to the modern definitions of the energy security. In the modern energy security, we are not only focusing on the quantity aspect of the energy that we can deliver, or any kind of our capability to provide the energy we are requiring for that. But also we are discussing about how far we can have any kind of balanced energy or high quality of the energy in the real-time manner. So in this case, when we are talking about the renewable energy is basically very, very fluctuating, especially like for the solar and wind, and also in demand side also for the demand of the energy, basically it's also fluctuating. So the big concern over here is that we are not only dealing with the capacity of the energy that I can provide, but also how far we can provide or deliver the energy at the balanced manner. And the balanced manner is very important over here. Finally, we need any kind of very responsive energy systems to provide high energy quality for our life. Otherwise, in case that we cannot provide this kind of balanced energy systems simultaneously, finally, maybe we can have any kind of fault in our electricity. Sometimes our frequency of the electricity jumps up and also jumps down, and also sometimes also the voltage also getting increased significantly or decreased significantly. And the second aspect is correlated with the energy equity. It means that how far we can also provide broader opportunities to all of the stakeholders, not only for the energy players, but also for the consumers. So basically all the stakeholders, including the consumers also, they have equal responsibilities. So it means that the consumer itself, or the end user of the energy, not only enjoying or behaving as the kings in the markets of the energy, but also we have any kind of responsibility to respond in real-time matters about the energy conditions. So it is also dealing with any kind of renewable energy, because renewable energy is basically widely and also thinly distributed, means that in case that we would like to extend or facilitate maximally the renewable energy which is available in the country or the regions, means that we need to also facilitate all the stakeholders to be able to provide or deliver their energy produced from the renewable energy. That also means that the open market for all of the stakeholders. And finally, also the third one is correlated with the environmental sustainability. I think all of you are also quite familiar with this one, but I just would like to remind that it is not only dealing with any kind of like CO2 or carbon dioxide, but also it is correlated with some other aspects, whether the soil quality, the air, also the water, food. Their correlations are very important. And these kind of three pillars in these energy systems finally are also very strongly correlated with issues in the Sustainable Development Goals. Some of them are really strongly correlated, but maybe some of them are quite weakly correlated. And when we are dealing with the energy, means that we are also dealing with how far we can provide the dreams for the Society 5.0 or Industry 4.0. But in Society 5.0, we are not only focusing on the transformations of the technology, but also how far we can maximize or optimize our players as the human is the main player in the transformations to maximize or optimize our creativity and also imagination from there. Finally, also not only solve the problems, but also create any kind of values in our society. So now we are in the transitions period for the energy systems. We are targeting to achieve carbon neutrality. That depends on this country. Some countries set by 2050, but some countries also maybe by 2060, like Indonesia, China, and also other countries are basically 2060. But some developed countries basically they set up in by 2050. So we are now moving for the market also, for the system also, we are moving from conventional linear economy to any kind of circular economy, means that how far we can minimize the materials and also the energy flow. So the materials and also energy feed to the system itself must be minimized, and also as well as the output from the system itself, including the waste and also the wasted energy or the wasted heat from the system, should be minimized. And finally, we need to maximize the circulations of the materials and also the energy inside the systems. So although the circular economy is not so wide compared to any kind of SDG or Sustainable Development Goals over years, but we can see over years that in case that we can maximize this kind of circulations of the energy and also of the material inside the system, means that at that time we can also improve the sustainability in the systems. So this is the when we are talking about the circular economy. So this is main key in the transitions to the carbon neutral. So previously we have the concept of from the cradle to grave, but now currently we are moving from cradle to grave, cradle to cradle. So it means that although the materials or maybe the energy wasted from one systems, maybe it can be any kind of important or crucial materials for the next systems, or maybe it can be any kind of energy source for the next systems. So we are moving the concept from the cradle to grave to any kind of cradle to cradles. So how far we can improve the values of the materials and also the energy, I think that's also very crucial for defining or achieving any kind of circular economy or sustainability in the future. So this is also the general roadmap for the decarbonization in Indonesia. We have figured out this kind of scenario. So we can start from any kind of reductions of the carbon dioxide, but in 2040, in 2050, we are expecting that we can also have any kind of ability or technology to capture the CO2 and also to utilize the carbon dioxide. So now the big idea for the carbon reductions in Indonesia, I think, by adopting the renewable energy and also doing any kind of deforestation and some policies correlated with that, including the carbon tax, carbon tradings, and also other policies. But the problem so far years is that for the carbon captures, currently it is very, very high. So the average carbon capture technology currently, I think the cost per ton CO that we need to capture is, I think, it's about $25 to $30. While for the carbon tax, like for Indonesian case, for the power generations, now the carbon tax is only $2 per ton CO2. Means that there's a big gap between the carbon tax and also the carbon capture cost. So we are expecting that by 2040, we can have any kind of lower cost for the carbon captures, and we can reduce the cost from about 20 or 30 US dollars to about 8 or 10 US dollars. So it's about 40% or half of the current cost of the carbon captures. So by that time, we are also expecting that the carbon tax also can be increased. So it means that carbon-based systems, carbon-based power generation or other systems, finally the cost for that also will be increased, and there will be any kind of competition, or maybe we can choose whether we would like to emit the CO2 or capture the CO2. So there will be any kind of fair competition between the carbon captures and also any kind of cost for or any kind of payments or penalty for emitting the CO2 at the times. So this is also, we have figured out also some possible roadmap to zero carbons for Indonesian case by 2060. And in these times, I think in this roadmap, we could see over years that we would like to break down the milestones for about 5 or to 10 years over years. And we can set up this kind of goals by adopting any kind of some technologies, including also the hydrogens, also renewable energy, some storage technologies, including pump hydro, and also some maybe we need to adopt also electric vehicles, electrification in the transportation systems, and finally, not only adopting this kind of electrified transportations, but also how far we can control it. In case that we cannot control our electric vehicles or any kind of electrified transportation systems, finally it also becomes any kind of accidents or any kind of big problems in our country. So how far we can tackle down this kind of problem, that's also a big concern. So I think by 2035 or 2040, we need also to develop any kind of vehicle-to-grid technology, or minimally any kind of coordinated charging, also discharging services for this kind of electric vehicles. Otherwise, it will be any kind of problems. In case that we have any kind of ability for that, finally, we can utilize also our distributed electric vehicles as potential energy buffer or energy storage. So we need also to develop any kind of open market for not only for the electricity, but also for any kind of energy that we can have, including also the chemical energy like hydrogen, ammonia, or etc. And finally, also maybe we need to develop any kind of nuclear energy by 2050. And although in 2060, it doesn't mean that zero carbon, it doesn't mean that we need to have any kind of complete or 100% renewable energy. No, we can still utilize any kind of fossil fuels or carbon-based fuels, but the problem is that how far we can deal with the emitted CO2. So maybe we can have any kind of offsetting technologies or offsetting policies, like for using any kind of direct air capture for CO2 captures. So we can have any kind of emission from power generation utilizing any coal or maybe any kind of natural gas. But other places, other times also, we can have any kind of carbon captures by utilizing DAC technologies. So it means that we can offset the CO2 emitted from the power plant. So this is also promising energy storage for Indonesian case, but I don't want to talk in detail about this one. This is also the possible adoption for the hydrogen in Indonesian case. Why hydrogen? Because I think in this case, hydrogen is also quite efficient for the power energy systems, and basically it is widely available. But the problem is that hydrogen is available in the oxidized state, so it means like the water. But the big things over here is that hydrogen has very good gravimetric energy density. It is very high. It's about 120 megajoule per kilogram, and I think that is the highest fuels or the highest gravimetric energy density that we have currently. And also, but the big problem for the hydrogen is that it has very low volumetric energy density. That's only 3 watt-hour per liters. So the problem for the hydrogen is that however we can have any kind of storage technology or transportation technology for the hydrogen itself to be efficiently stored and also transported. So we have several options for storing the hydrogen, including liquefactions and also maybe some reforming technologies to ammonia, to any kind of organic carriers or etc. And also adsorptions, compressions, etc. So we have several options for the hydrogen or ammonia applications, not only dealing with the transportations. So I just would like to remind that the big scenario over here is not only utilizing the hydrogen for the transportation, but I believe that for the transportations, the demand for the hydrogens or ammonia is very small. It is significantly smaller compared to any kind of power generation or industrial use for the hydrogens. Like for the steel making, basically hydrogen also can be used to replace the currently utilized cokes for the steel making. So hydrogen can behave as the fuel as well as also for the reducing gas in the steel making industries. But for the transportations, I think there will be also a huge competition with the electric vehicles. So as I mentioned previously, the good characteristic of the hydrogen is that it has very high gravimetric energy density, means that for the transportation that needs very high gravimetric energy density prefers to utilize hydrogens. So we can utilize hydrogen for the aviation, for the airplanes, for the ships, maritime ships, and also for any kind of huge or large-scale transportation system like train, buses, trucks, or etc. So we have also like integrated systems utilizing hydrogens, electricity, heat, and also other things. So this is the possible roadmap in general for Indonesian case. Things we can start to have any kind of demonstrations, or maybe how far we can increase the social acceptance, how far also we can increase our positions in the export and also import market for the hydrogens. Now, because currently, like Australia and also Brunei, Darussalam, they have started for the export and also import market for the hydrogens. They would like to have like for Australia, they are now building any kind of project for large-scale hydrogen production from coal and also transport the hydrogens to Japan. So it means that it will be the first largest global and hydrogen production, also transportations. And the second period will be the infrastructure developments. I think this is very crucial for us. And during this kind of infrastructure development means that at that time maybe we cannot expect any kind of profit or hydrogen economy at that times. But after building the infrastructures means that at that time what we are expecting is that we can create the market and also we can get any kind of economy or profit from this kind of systems. So there are also some application roadmap in Indonesian case. So we are not only, as I mentioned previously, that we are not only targeting for any kind of transportation, but our target is over years. So large-scale utilization for hydrogen, including also for the power generations, industry, including for the steel making and also cement industries, and also for the large-scale transportation systems, and also finally also for the distributed energy system, including also for the residentials, including housing or etc. And from now on, I think it's about 10 minutes or something like that, I just would like to talk about some correlated technologies, especially correlated with artificial intelligence, also digital twin technologies, or any kind of machine learning technologies correlated with the hydrogen-based energy systems. So now we are talking about the digital transformations in the energy system. Means that all the stakeholders, including the energy producers, energy consumers, energy operators, between the producers and also the consumers, they have any kind of big data. And finally, this kind of big data can be processed by any kind of artificial intelligence to produce any kind of like decisions and any kind of suggestions to all of us, or maybe it can also control the system by itself. So like what Google has done in 2012, 2013 is that they utilize any kind of artificial intelligence, especially machine learning over years, to control their energy system inside the Google offices. So finally, they can reduce the energy consumptions by about 30%. So I think that's really huge. So
you have
in general,
7 minutes left, Prof.
Okay, sure. So we need to share all this kind of big data and also finally share this kind of markets together. So we need to have any kind of open market finally in the future. And when we are talking about digital twin technology, why it is very important, because when we are talking about the energy systems, like Professor Ariando also mentioned previously, I think finally also we need very, very big systems and also very sophisticated systems. So the parameters getting much more, there are many parameters correlated with this kind of energy systems. And for the digital twin technology, we need to combine together between the virtual world and also with the real world over years. So this including how far we can utilize this kind of big data, cloud computing, extended reality, artificial intelligence, also any kind of monitoring technology, including Internet of Things. So like for the power generations, means that when we are dealing with any kind of power generations over years, and we would like to change, or we would like to optimize the operation for the power generations, when we need any kind of, when we do any kind of simulations or maybe any kind of experimentations, basically it takes very long times. But by utilizing this kind of digital twin technology, we can have any kind of real-time predictions over years, and we can have much more faster decisions and also suggestions for all of us. So there are some possible applications of artificial intelligence in the energy systems, especially not only classifying what kind of the system will be, but also projecting or predicting what really happens in 5 years, 10 years, or maybe 100 years in the future. So it is also including the micro and also micro scales of the applications in the energy systems, including like for small scale power generation and also maybe one country or maybe global energy systems in the future. So this is also only the examples, the application of digital twin in the power system. I just would like to skip it. And so there are some applications in digital twin in the energy systems, including the prediction, blah, blah, something like that. And also we have also developed some methods for utilizing artificial intelligence for predicting the energy systems. That can be any kind of rule-based, model-based, but finally also, which is the ultimate work of us, is that we have done any kind of model-free based prediction system. So we didn't lay further for the model base that we need to develop, but also the systems can optimize by itself, or maybe can predict by itself. So finally, we can have and we can measure what really happens in 5 years or 10 years in the future, in case that we are taking any kind of policy now currently today. So we have also developed some MILP methods, some reinforcement learnings, and also for the model-free systems. Also, we have dealing with any kind of deep reinforced learning methods, and also we have also developed by ourselves, including the double deep Q network algorithms for here. So because we are dealing with any kind of different systems over here, and also finally also how far we can develop any kind of reinforced learning, which are quite sophisticated, because we are dealing with several parameters or many parameters over here. And finally, what we are expecting is that the systems can optimize by itself. So we can set up any kind of objective functions, whether it is much more focusing on the efficiency of the energy, or maybe for the economic performance of the energy. So we have done several studies also, and also we have done also several studies, including some countries, how we can have any kind of like hydrogen-based or renewable energy-based energy system, which is optimized in several countries, including in China and also in Japan. And also we have done also related with a digital twin in the combustion technology of the hydrogens. The problem for the hydrogen combustion is that the flames of the hydrogen combustion is in the area of ultraviolet region. So it means that our bare eyes cannot check or cannot see the flames during the combustions. It is really different with the carbon-based fuel, because usually we can check any kind of reddish or red flames when we combust any kind of natural gas or maybe wood-based fuels. So over there means that there will be any kind of problems in case that we cannot check the flames, what really happens inside the combustor. So what we are developing over here is that we are developing any kind of advanced simulation technology to predict accurately the combustion inside the combustors. But the problem for the simulation is that it takes very long time. Although we use our supercomputers, Fugaku-based supercomputers in our simulations, for one condition of the combustion, it still takes about 2 to 3 weeks for simulation, because it is very resource intensive. So to have any kind of digital twin technology to be applied, we need to have any kind of much more real-time predictions. So finally, we develop any kind of neural network technology to predict that. So we utilize the database that we have built on the based on the simulation and also the experimental studies. And finally, we are dealing with any kind of PINs, physics-informed neural network, to predict accurately what really happens during the combustions. As I think previous, there was any kind of questions correlated with how far we can increase the accuracy when we have any kind of low quality of the data over here. What we have done over here is that we are not only using the data over here, because we know that to create the data is also another problem. I mean, for the simulation, as I mentioned previously, that we need about 2 or 3 weeks for one conditions. So to create like 110 or 1,000 of data, maybe we need about 10 years for that, for simulations. What we have done over here is that finally we are combining between the data driven and also with the information driven. So for the neural network also finally we are combining our data over here And also we are combining together with any kind of basic information, including any kind of fluid dynamics, any kind of chemical mechanisms over years. And finally, there will be any kind of balance between the data-driven and also information-driven. So in case that the data are quite limited or the quality is not so high, finally the informations, the neural network or the prediction itself is mainly driven by the information, by physics, chemicals, blah, blah, something like that. And in case that what we really expect is that both the information or physics information and also the data, they have quite good quality. And finally, we can have much more accurate predictions by the pen itself. And this is the last slide for my talk today. I think there are some issues that we need for in this case. I think we are not only needing any kind of technology, but also the big problem for us is that how far we can have any kind of feasible and also measurable and also doable roadmap for our energy systems. And also finally also how far we can create to be inclusive to all of us, to all the stakeholders. We need to create any kind of open market together. And also regarding the capacity building for all of us. Thank you very much for all your attention today. And I would like to welcome in case that there are some questions. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you very much, Prof. That's very nice presentation indeed. Ladies and gentlemen, because of limited time, we only open for 2 questions. One question from this room and one question from Zoom. Raise your hand if you have. Okay, Henry, and from Zoom. Is there any question from Zoom, please? No. Okay, for Henry.
Okay, thank you, Dr. Ahmad Marzuki. Thank you very much, Professor Aziz. Very interesting presentation. I have one question, Professor. As Professor Aziz and Professor Ariando talked today, Professor Aziz talked about how to connect the digital technology to the energy application, and Mr. Ariando how to connect the how to say like artificial intelligence and so on to the quantum material. So my question is simple, Sensei. Sorry. My question is, what the competency so our students have today's digital era? That's thank you.
Okay, that's from Prof. Henry. Okay. Prof. Aziz? Yeah.
Oh, okay.
Only one
Thank you
question.
very much. Okay, Prof. Henry, thank you very much. It is very difficult questions. So I just would like to answer based on my opinion and also based on my experience. So for the competencies, finally, what we really need is that finally the basic competencies, that's including how far we can understand the basic rules or the basic things about the science itself. And also finally, it's about the imagination technology and the imagination capacity. I think that's very important. So the imaginations, motivations, and also I think these 2 things I think is very important. So imagination, how far we can imagine in the futures. I think this is very, very important for all of the students, especially not only for the students, but also including also the faculty. I think that's also very important in general researcher itself, I think. And things like for digital one, because Professor Henry mentions about the digital things. So finally, maybe I can share some things that when I had discussions with one of the experts in Japan when we discuss about the supercomputers, because he is expert in supercomputers. What he is thinking about in the future is that language is the barriers. So he is thinking about something that maybe some other peoples are not thinking about it. So he thinks that maybe in 30 years in the future, 50 years in the future, we don't need any language anymore because the language is also the problems. So he mentions that finally all the languages and also finally all the things that we are thinking about can be digitalized. And finally, in case that we can have any kind of communication, direct communication in digital manner, finally the language or any kind of communications can be completely defined together, can be completely transferred from one person to other persons. That's, I don't know whether it is really feasible in the future or not, but what I really respect to him is that he has any kind of imaginations that maybe some people are not thinking about it. But also he has any kind of reasons behind that, or very strong rationality for that. So I think for the digital technology like now, I think the big things that we need to deal with is any kind of imaginations. So whether this kind of imaginations or dreams can be realized in the future or not, I think that's another problem. But I think for the students, for us, the faculty, as the researchers, I think the big issue is that how far we can have very good or very excellent imaginations itself. Thank you very much.
Okay, thank you very much, Professor Muhammad Ais. Ladies and gentlemen, because of limited time, we have to stop this session. Oh, if you have one more question? Oh, there's one more question from Dr. Surja.
Yeah, thank you, Pak Dr. Ahmad. The question is for Professor Aziz. I saw your presentation that in 2060 we will get the net zero emission. But if I saw in the IPCC report that for the RCP representative concentration pathway, even for 2.6, RCP 4.5, RCP 6, RCP 8.5, in 2060, is still a high concentration of the hydrogen, concentration of the carbon concentration, and also all the gas. So maybe you need to, or this is maybe our duty to calculate again. In 2060, maybe it's not. We cannot get the zero emission. I think like that. Thank you, Professor.
Okay, thank you very much, Dr. Surja, for your very nice question. Actually, yes, my direct answer is yes, actually. So why I draw any kind of roadmap over there is that's very, I think the government has set up carbon neutral by 2060, and I think it is very hard for us to achieve that. Although for Japan would like to have carbon neutrality by 2050. Whether it is really possible? No. Every people thinks that it is impossible. So for other countries also impossible. And that's, I think all people are known about that. But the problem over here is that how far we can motivate ourselves. And for the carbon emissions, I think carbon emissions will be emitted. Carbon dioxide will be emitted, not also together with other gases. When we utilize also the hydrogens or ammonia, finally, not only emitting CO2, but also NOx. That's also another problem for the emissions. But what we are dealing with over here is that how far finally, the big things over here is that we can reduce significantly, and also we can adopt any kind of offsetting technology or offsetting also policies over years. So that, I think, the big motivations over years, the carbon emissions finally cannot be avoided. So we still, I think 2060, we still consuming any kind of like fossil fuels, coals, natural gas, oils, or etc. We cannot avoid it because that's also the potentials. And also we have big infrastructures for that. We cannot just abandon this kind of infrastructures. And finally, also the big things over here is that how far we can motivate ourselves to capture, to do any kind of offsettings, and also to utilize it. Because the problems with the carbon captures is that finally it is very difficult to store or to sequester the CO2 itself. And I think the discussions about this CCS or carbon capture storage just, I think it has been being hot in 2010, something like that. But because of the problems during the storage, and finally people cannot deal with that, finally the idea shifts to any kind of carbon utilizations. And now, although we can utilize the CO2 for any kind of like materializations or maybe mineralizations, the problem is that it still also consumes the energy. And finally, also, that's also another problem for all of us. But finally, we need to motivate ourselves how far we can reduce it, and also doing any kind of offsetting, and finally also to utilize the carbon dioxide that we emit together. Thank you very much for your very nice questions.
Thank you very much, Professor Muhammad Aziz. Ladies and gentlemen, I know that there are more questions, I think, in the Zoom, but because of limited time, we have to stop this discussion. And if you have any more question, please send that question directly to either Professor Ariando and also Professor Muhammad Aziz. Is it okay, yeah, Prof? Yeah? Okay. Okay, now thank you very much from everybody, and also thank you very much for Professor Ariando and Muhammad Aziz. And please give applause for them, please. Okay, thank you very much, and I give the time back to the Master of Ceremony. Thank you very much.
Thank you very much, Dr. Ahmad Marzuki, for being the moderator for the first session of plenary lecture, and also Professor Ariando and Professor Muhammad Aziz as speaker for first plenary session.
Ladies and gentlemen, so we have here now continue to the second session of the plenary lecture today. So we have with Professor Ramesh Kashi and also Professor Agus Supriyanto.
This session will be led by our moderator, Prof. Nuryani. Prof. Nuryani graduated from the Physics Undergraduate Program Universitas Brawijaya, Physics Graduate Program Universitas Indonesia, and completed his doctoral education at the University of Technology Sydney in field of electrical engineering. Currently, he is occupied as lecturer in Physics Department, Faculty of Mathematics and Natural Science, Universitas Sebelas Maret. His research focusing on magnet material and sensor, electronic and instrumentation. Please give a round of applause to Prof. Nuryani, and the time is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone, ladies and gentlemen, distinguished guests, and also fellow attendants. A warm welcome to this plenary keynote session, where we have privilege of hearing from two distinguished speakers. I am honored to be your moderator to this event. First, let's start for introducing our first keynote speaker. He is Professor Dr. Ramesh Kashi from the Department of Physics at the Faculty of Science, University of Malaya. Dr. Kashi expertise lies in the world of nano-composite coatings, which represent the future advancing coatings. He has a remarkable academic journey, serving as a senior lecturer at the Physics Department since 2010 and earning the title of Associate Professor at 2017. Dr. Kashi is not only a dedicated educator, teaching both undergraduate and postgraduate students, but he has also supervised graduate students in their research endeavor. His work primarily revolves around electrochemistry application in polymer materials, particularly in the realms of energy storage system and corrosion. It's worth noting that he has guided and mentored in a significant number of PhD and also MSc students, with several more currently pursuing their degree under his capable guidance. Today, Professor Ramesh Kasi will share his insights in the presentation title, Nanocomposite Coating, a feature of next-gen coatings. Our second keynote speaker is Professor Agus Supriyanto from the Department of Physics at Faculty of Math and Other Sciences, University of Sebelas Maret. Prof. Agus Supriyanto got PhD from Gajah Mada University, Yogyakarta. His current research is focused on the optimization of Gambier day and hybridization of Ag metal to enhance the performance of DSSC-based solar cell. With his expertise in this field, he shed light on ways to improve the efficiency of this energy harvesting device. His work is essential for advancing sustainable energy solution. Okay, for the first speaker, so is Professor Ramesh Kasi. So I call him. Hello, Professor Ramesh Kasi.
Good morning. Yeah, good morning.
Good morning. Okay. Okay, thank you, Dr. Kasi. So the time is for you, and the virtual seat is yours. Please, Dr. Kasi.
Can you see my slides?
Okay.
Okay. Okay. First of all, thank you so much, everyone, and especially to Professor Budi for inviting me for this wonderful occasion. Unfortunately, I couldn't attend this meeting because I was selected to represent our university in the state level competition. So I'm today until tomorrow. So sorry for that. So I have attended this another conference in UNS in June. It's a wonderful experience. Now I'm wearing this shirt, birthday shirt, presented by the department. Thank you so much. I miss this opportunity to be there again. Thank you so much for that. Okay. Before I go to my topic, I just introduce Malaysia. I think it's a very wonderful country, and you can see beautiful places all around in Malaysia. We have different islands like Langkawi, Penang, and you can see like we have Birthcase, the tallest statue of Lord Muruga, and other beautiful places in Malaysia. This is the national mosque in Putrajaya. This is our capital, administrative capital of Malaysia. Okay, and then I introduce our university. University Malaya is the top one in universities in Malaysia and number 3 in Southeast Asia. And we are the 65th in the QS ranking 2024. So this is our university chancellery building where all this administrative work is going on. This is our Faculty of Science, and we are here as the Department of Physics. So we one of the oldest and best university in Malaysia. Okay. Okay. Before I go to the topic, these are my outlines of the topic today: introduction, history of graphene and corrosion, and research objectives and methods, research and discussion. Okay. Okay, now we all know about the corrosion. Corrosion is an electrochemical process, but when we go outside every day, even in our home, you can see a lot of places like brown color thing. So that's basically is corrosion. We may think it's a small issue, like okay, we can do some coating and then we just pour water. We just imagine it's a very small thing, but actually it's a huge and a very impactful phenomenon that lost a lot of lives every year. You can see these three figures, a pipeline blast in few years in the history. Even maybe somewhere it's happening, building collapses and bridges collapses. Why it's happening? Because the corrosion is maybe outside. It may be a general atmospheric corrosion, but inside that maybe a pitting corrosion may happen. So I will explain what are the types of corrosion later. So when pitting corrosion, you cannot see from outside. So that inside part may be eaten up by corrosion product, then wash away, then sudden fracture. Some ships have been collapsed due to this corrosion. So it's not only economical concern, but also like life concern. Many, like you see, these environmental issues, the sea, fauna and flora, all affected due to this oil leakage, due to the corrosion in the pipelines. Okay. This is a general, small, basic, fundamental how the metal corroded. So that will be, basically it's an electrochemical process. Oxidation and reduction happens simultaneously. When the metal exposed, immediately it becomes oxidized, so releases electron. The surrounding with water and oxygen, they become a cathodic reaction, gives you a OH minus, that's a cathodic product. Then these two react and then gets the metal oxide that is called corrosion. Okay. As I said, it is a big market. Every country, 4 to 8% of the GDP they spend to replenishing the structures damaged by corrosion or restructuring these collapsed buildings. So every country they are spending like 4 to 8%, around 2.5 trillion of money is spent all over the world. So now, to avoid this, or we cannot avoid corrosion. Why? It's a natural process. Natural process meaning we extract iron or aluminum or other metals from the earth crust as in the form of oxide. So naturally, the material we develop or purify become metals. Then naturally they intend to go to the original state, which is oxide. That's a form of corrosion product. But what happens by nature, they make the passivation layer on the surface as an oxidation layer, like metal iron oxide, aluminum oxide. When you see the aluminum plate, you just come from washing, you can take the particle, you can see the white color particle, which is iron oxide. But if they are uniform in nature, they will protect the metal itself. But if there is any dirt accumulation or water droplet or any other crack or something where the corrosion initiation happens, that will lead to the complete damage of the material. So now, this you can see this bottom graph, the cumulative growth rate of manufacturing of coatings is 4.5% during this year, 2018 to 2026. So you can see Asia Pacific has a leading market share around more than 50% of coating industry. A lot of coating industries in our Southeast Asia, like big companies have plants or production units or head offices in Malaysia, Singapore, Indonesia, Thailand, and so on. So we are leading manufacturing our market size for coating. So there's a huge market in future. Okay. Now, as I said, there are corrosion. Corrosion had for different forms of corrosion. The general form is atmospheric corrosion or environmental corrosion, where we see the outside structures becomes a brownish in color. So this is just exposure to the atmosphere, they react. But there are different special corrosions like galvanic corrosion. Galvanic corrosion, when we connect two dissimilar metals like zinc or copper, like brass, alloys. I hope you all heard about the carbon sponge. So copper sponge. Copper sponge is like you take an alloy, combination of copper and zinc. So you put an acidic solution or water solution. So what happened? Zinc is more reactive. This electrochemical series. Zinc is more reactive, so they oxidize fast and leach out from the copper, the brass, aluminum material. So what happened? All the zinc is leached out, then we can get the sponge, copper sponge material. That's due to the corrosion. Then this is a galvanic. Then we have a reverse corrosion where these planches and connections, the small area where you cannot reach that area where this cathodic medium like liquid and electrolyte will accumulate, so the corrosion will take place, so that we cannot notice. That may lead to the damage. And pitting erosion, as I said, the surface will be very uniform, maybe small pit inside, but there will be a big corrosion process happening underneath this pit, and then the whole area will be eaten up. So pitting erosion. Filiform corrosion is kind of corrosion where we use like a lot of soft drinks cans. So people coat the sticker, the bread sticker on the surface, but inside there will be a corrosion will happen. It forms filiform in nature. And grain boundaries occurs for the different alloy materials, and as well as the stress corrosion process, like when this material will be continuously used, cyclic stress on the surface, also exposed to the environmental, maybe acidic or base or aqueous solutions. So that will be lead to stress corrosion cracking. Then other one is fatigue corrosion, also like the material is continuously working under pressure, under stress, like shaft and so on. They will lead to fatigue corrosion. So now, there are many methods available to prevent corrosion. So corrosion, as I said, it is not a small issue. People are working hard to prevent corrosion. We cannot stop corrosion, but we can prevent corrosion effect. Basically, first one is the selection of materials. How we are going to protect the material is you select materials. What application, what material you are going to use. Nowadays, composite is a Guardscape. I think the researchers very good innovation is the composite materials. Previously, we use all the heavy metals or metals to apply for all kind of like bicycles, tennis rackets, and then you imagine whatever application now, they are lighter and very strong. That's thanks goes to the composite materials. Selection of materials is very important. The second one is alloy. Like our utensils for cooking purposes, we use a lot of stainless steel materials and aluminum alloy materials, because we use cast iron or normal iron Fe only, so it will corrode. So now we are using like stainless steel 3.303 and other grain materials. So because we want to avoid corrosion, because to avoid some effect to our body. So alloy for many purposes, not only for cooking utensils, other purposes also, like in aerospace applications and marine applications and various other applications, so we use alloy. And the other one is the cathodic protection. Cathodic protection, we have two types of cathodic protection available. One is the impressed current system, another one is the sacrificial anode system. Impressed current system, you apply, let's say I was talking about the pipelines, right? So pipelines of water or gas or oil underneath this water, sea or land. So they must be protected. There are many ways people are using to protect. First of all, they do coating. So when coating can prevent corrosion, but for underneath, there will be a lot of changes going on, like some damages on the coating. So it is not guaranteed to prevent the material of interest for longer time. So what people do, they do is cathodic protection. Cathodic protection, you apply potential, is impressed current system. You apply potential, that means electron will be surrounding this pipeline, where the cathodic reaction at the nearest area will happen. So they utilize this electron instead of the ion or the material of interest will oxidize and give the electron. So the feed is given by the impressed current. The second one is a sacrificial anode system, where pipelines are laid out nearby the anodes, like the more reactive anodes. Example, we have steel iron pipe there. So people will lay magnesium or aluminum anodes materials. So to provide electrons. So because when you connect to these two different materials, the highest effective or active material will react first, oxidize first. So they give electron, the cathodic reaction completes, then our material is protected. So the best method is corrosion resistant coatings. You may hear about the powder coatings, metallic coatings, thermal spray coatings, and so on. These are like very specific applications. Also, they are very expensive. The best method is organic coatings. Organic coatings, we know all the normal paint coatings in a wall, wood painting, or sail painting. So they generally use organic resins. Organic resins you name as acrylic resin, epoxy, polyurethane, polyester, silicone resin. Also, we now use natural rubber-based materials and base materials converted into coating materials. The researchers are doing to not only use a single system, like only with acrylic or only with epoxy. Now we are working with blending of different resins to get optimized properties for multifunctional properties. Like it's not only for decorative purpose, not only for corrosion resistance. It also, like, coatings we apply, maybe our house paint outside, exterior paint, maybe first day or first year will be brighter in color. So maybe second year, the fading happens. This is due to the UV effect or temperature effect. So we are incorporating different aspects of our preferences or our requirement to be enhanced by adding various compositions. Like we are trying with a combination of resins or adding additives, or now the new method, hybrid composite coatings. Hybrid composite coatings, we can have a different pigments, but nowadays the nanotechnology comes into picture and gives us more solution. When the size becomes lower, the effectiveness of the material becomes higher. So the size matters. So now we are adding nanomaterials into the coating. Then we can reduce the size of the thickness of the materials. We can reduce the amount of the material coating, reduce, then it leads to the reduction in the cost of production and cost of applications. Okay. Now we talk about this organic coatings. Now, how we have to see how these coatings prevent the corrosion. So basically, first one is just a blocking effect. What blocking effect? You just make a normal coating, thick film coating, then it will not, make sure there is no pore on the coating surface. If pores, then the electrolyte can penetrate and reach to the interface and corrosion will be initiated. But when you have a intact coating, so there's no possibility for electrolytes or electrolyte materials to penetrate. Then another way is anodic passivation, like a zinc primer coating and anodic passivation, as I said previously, the metal oxide formation on the substrate due to natural reaction. But if you have any breakage, then it will be a problem. So what happened? We must make a passivation layer of the same material in oxide form. We coat, then we coat on the normal coatings on the top. Because previously people use primer coat, intermediate coat, and top coat, and final finish coat. So now we try to do with a single coat method to reduce the manpower, reduce the amount of material that we use. Cathodic passivation usually is a zinc primer. So where see the gray color paint, first of all, they apply on the steel plate because they want to make the cathodic protection, because zinc is more reactive than the metal substrate like iron. Then self-healing, another way, people are working to using self-heal. Self-heal, if the coating is damaged, so it heals itself by many methods, like encapsulation method. We put monomers inside an encapsulated polymer. Then when they cut the monomer, they react again, they join, and then the film is grown by itself. And then there is a missile field healing media. Some other materials will be added to make the gap to be connected with the cutting area. So like technology is going and growing, and then to lead to new technologies. Okay, now what we do, there are many issues with the organic coatings. Why? Actually, our purpose is to isolate the material surface through direct contact within the environment. Then, first, we need to make a barrier protection. So just block. Then, other important thing is adhesion properties of the material. Adhesion is, what is adhesion? The coating substrates there, you apply the paint, it must stick to the surface. 70% of the coating failure is due to the adhesion failure. So this is this research is carried by ISO. So they said 70%. Maybe like we have seen sometimes our ceiling paint will fall suddenly without any reason, because there will be a delamination from the substrate and the coating. So due to the adhesion force, because there will be hydrogen bonding between the surface and the coating. So sometimes you don't provide proper material to improve this adhesion, so they will delaminate and fall off and the coating fail. Okay. What is the current problem that we face in this coating? Because most of the polymer, sometimes they cannot withstand to high chemical resistance. After you coat, you can see the bubbles or the pores on the surface. And then they also, like as I said before, they cannot withstand against this UV and temperature and hydrophilicity. Hydrophilicity actually is a wettability property where the contact angle of this coating must be lesser than if it is lesser than 90 degree, it is hydrophilic in nature. Hydrophilic means water attraction. More than 90 degree is hydrophobic in nature, or water repellent, and more than 150 degree is super hydrophobic, like lotus effect. So a lotus leaf, if you pour water, it will not stick to the surface. It becomes a droplets. So it's a complete water repelling, because the surface is more microfibers or nanofibers there. So there will be air pockets inside this lotus leaf or the helix. Then they water pockets, they push the water away, then they make spherical particles. So that's also we want to improve this in this research. We want to improve this. Then another one, single functionality. As I said previously, just only for decoration purpose, only for corrosion, only for these things, heat resistant. But we want to use multifunctional properties, so which can be improved by nano composite techniques. So also we plan, we are working towards the volatile organic component reductions. So when you can see a new coated buildings or a new car, you can see a very bad smell, a stringent smell. This is due to the solvents used in this coating evaporate immediately. They will be damaging our breathing system because they are toxic in nature. So we also working towards to reduce the amount of volatile organic compounds, because they are dangerous. Also there will be norms to reduce that. Okay. What we do, we want to have a sustainability in coating industries, like one-stop coating solution. We want to provide a single coating system to obtain multifunctional in nature. So also natural curing. So some coatings, they need some kind of special process like heating, radiation, and so on. So to cure is drying. So drying, not only just dry, but it must dry completely. That means there will be cross-linking between these polymers happen. So we also need to focus on it, because it will lead to the adhesion properties. And multifunctionality, as I said, transparency, heat resistance, corrosion resistance, thermal resistance, and what we call decorative purposes. Okay. Nano materials, as I said before, the nano, not only name is hype, what we call, it is not only the name that people are talking more about, but actually it has a better effect on this in material science. So we have tried with the particles, titanium dioxide or silicon dioxide in micro sizes, in micrometer size. During my PhD time, I used nano titanium dioxide for heat resistance to around 10-20 microns, but they cannot withstand the corrosion resistance around 10 to the power 6 or 7 for 30-40 days. But now we are working on with nanoparticles like less than 100 nanometer size, so they can withstand with the 10 power 10 or 10 power 9 ohms until 90 days of exposure. So we have proven that nanotechnology has contributed a lot in coating industry. So it's now we are working on not only this size and then the amount, the fractions, percentage or loading ratio of nanofilters, how the affecting the coating system, the post matrix. So I just want to share that what are the novel contributions that we have done during our research. We have prepared acrylic silicon polymer matrix with silicon dioxide and ZNO, zinc oxide nanoparticles. So we improved hydrophobicity more than 130 degree, and transparency is 90% transparent with UV with spectroscopy studies. Thermal stability, my PhD work, I use silicon polyester around 400 degree centigrade with a titanium as a pigment. Now we are working with 600 degree centigrade to withstand higher temperature for high temperature application, the same kind of coatings. And superior adhesion, we have tested these adhesion properties with ASTM standards. They withstand like 5B standard. So 5B standard is a standard given by this ASTM. So we proven that they are having very good excellent properties, which these are the papers have been published in Q&A papers in ICSAS. Then sustainability in the coating industries, like we prepared multifunctional coatings. What we have done, we use a bio-based materials like extracts with banana peel and extract from henna. We use as a corrosion inhibitor blended with our coating resins. That's one project, it's already published. And we prepare like, PET bottles, like the soft drink bottles have been crushed and then extracted these polymers. And then we added as a reinforcing agent with these polymer resins. Then that paper also has been published. And we use soybean oil as a modifier to the polymeric matrix. That work has been published by our final year project students. So now we are also working with the industry partners, air conditioner company. They have an issue, the corrosion at the fins, the junction of fins on the heat exchanger surface. So they cannot prevent because the area is very, very small to clean that area. So they approach us to develop coatings. So we develop coatings used on zinc oxide particles. Then we use a spray coating because spray gun, it can be reached out to if you put spray, the area can be covered with our coating. We tested the corrosion part. They works very well. They are now working with this because thermal stability and thermal profile studies is going on under inside this company for the air conditioner company. They are satisfied with our product. Okay. Now we use different nanoparticles like zinc oxide, titanium dioxide, alumina, other few more pigments we already used. Now we are working on with graphene and graphene oxide because it's graphene generally used for electrochemical energy side. So, but we have read some papers that graphene also can be used for coatings. So we are working on graphene. Graphene, is a form of carbon materials. So Game and Novoslav, they found out this graphene material is a wonderful novel material with a 2D structure. They help in many other applications. So mainly their properties such as thermal stability, chemical inertness, and tough, mechanically strong, and other properties makes us to use graphene for protective coating system. These are the
Excuse me, Prof. 3 minutes more. You can finish.
Okay. So these are the basic properties and applications. Graphene got various applications of different way like corrosion or microwave, medical and mechanical wear and tear applications. So these are this shows that how many layers of graphene added and how this other materials in graphene has proven that a single layer also can give better resistance. So this is the introduction. The Nobel Prize has been given in 2010 for the innovation of graphene material. So I just keep these fundamentals. Okay. Okay, this work I just explained maybe like one system. We mix acrylic and epoxy system. So we blend it and then we add a graphene. We said we study this binder. We call binder system a backbone of the coating. Coating contains four main things: binder, pigment, additives, and solvents. So we work on all the four items. So we blend epoxy and acrylic resins, and then from test all these properties, then we just added and graphene or graphene oxide separate system. This study actually got four different systems like graphene oxide, titanium dioxide, but I just explained one system and then putting it stopped. So these are the resins that we use, and then this is the nomenclature for this material names. And we use a polyisocyanate as a curing agent because when we are blending two different resins, you must have a coupling agent to make the coating to cure cross-link. So isocyanate, polyisocyanate, NCO, that's the ratio that we are used to prepare the coating. So these are the coatings. You can see some T1, T4, T5, T8, T6, T5 are very clear uniform coating. These coatings due to the highest concentration or improper mixing of the coatings, this is also called coating failure. Okay. From the test, what we did, we found that maybe this one I can skip. Okay. I explained this FTR study. So when you want to study this cross-linking nature of this coating, FTR, Fourier transform infrared spectroscopy is the best. You can see here, around 2280, it is actually a functional peak for isocyanate, NCO. But you cannot identify any peak in this area. That means all the isocyanate that we use has been utilized for the cross-linking. So there will be a new peak such as CH, NH, okay, here NH band at 1517. So this shows the new bond NH formed because previously there is no NH bond in this, any blending because we have epoxy, we have acrylic, NCO. But there is a new peak NH is formed 1517 as well as you can see somewhere here, the water, the OH group area also is NH. So you can confirm this NH is formed. So that says that all the material has been cross-linked completely. As I said, the thermal resistance, you can see after 400 only there's a third degradation peak starts. So that means our material can withstand higher temperatures. And transparency, as I said, we can say more than 85 to 90% after adding this, blending these polymers. But some composition, transparency is lesser. So T5 and this T1, they have a highest transmittance. Contact angle is only this blending of two resins. You can see some coatings more than 90 degrees. So that means we already have reached hydrophobic. But when 100% of acrylic and 100% epoxy, they are 50 to 60 degrees. Okay, this is the cross test to verify the adhesion properties. So T1, T5, T7, they have 5E in nature as per the ASTM standard D3359. Okay, this is called electrochemical impedance spectroscopy, which is a very essential method. We stick a PVC pipe on the substrate and pour 3.5% sodium chloride as an electrolyte, simulate the seawater. We perturb the system with 10 millivolts and then we measure the impedance. So this is called the Bode plot, modulus of Z, impedance versus frequency. Then you can see here the resistance is more than 10 power 10 ohms. So it is for day 1. Okay. Here, even this is day 60 also is still in this range, 10 power 10. That means there is no pore formation or there is no electrolyte penetration as the interface. Then that shows our coating. This is a Nyquist plot where imaginary impedance and real impedance. So you see, if you have a straight line, that means still in capacitive nature. If you have a semicircle, the other coatings, you can see this coating is failed. T4 is failed. You have a semicircle and a spike, that means coating failed. You can see here both also, there's a spike and then there's a plateau station. So that means coating well. Okay, now I go to the system 2 with the graphene. Okay, we add graphene here. You see 99 point, all the coatings are adding 1 to 7% of graphene. The improvement, you can see the improvement of graphene, 99.75 is become more and more hydrophobic. But graphene oxide a bit reduced because maybe absorbing some water, so the contact angle lesser. So I can show the dispersion of this graphene and graphene oxide in this mixture is uniformly blended. So this is also the EAS. So, okay, I think I can stop here because it's a lot of results, maybe similar results. As I can say, to conclude, the binder system itself, they become towards the hydrophobic nature. And we add G and GO, less than 1% of G graphene has tremendously increased the properties of the coating. And we add another component, TaO2, because we can add TaO2 or other color pigments that you want to add. You can add minimum percentage to increase the coloring nature. Or you want a transparent, you just use the transparent coatings. So we have proven that nanocomposite or coatings, the addition of nano materials inside this binder system has enhanced the properties very well. So we are still working on with other natural rubber, as I said, current final projects too on PhD working on natural rubber materials. Also, recently I got one tin grant from our tin research board of Malaysia. I got a new grant. So we are working on the natural resources from Malaysia. Okay, finally, thank you so much for giving me this opportunity. Also, we welcome everyone to visit Malaysia. Also, we have a lot of opportunities for collaborative research. So you can find my profile in UMExpert. You can type Ramesh Kasi. Then anytime you can contact me for any future collaboration. Thank you so much.
Thank you very much, Professor Kasi. This very nice presentation and also interesting. Now the discussion session. So please, any question from? Okay, what's his name? I forgot. Diani. Okay, Diani. Yeah, please, Diani.
Hello, good afternoon, Professor Ramesh. My name is Jenny Gali. So actually, when I was in a bachelor degree, I have experiment and research on the polymer. What I know is about the coating. It's mean organic coating. So that's why my questions will be about the organic coating. So my question is, what are some emerging trends in organic coating technology, and what are the potential application of these emerging technologies? That's all. Thank you.
Okay. Thanks for your question. Emerging technology, now you can see, like, first of all, previously we used a lot of solvents. As I said, what you call the smell. Now people going for water-based coatings. So we changed organic solvent into water-based coatings. And also, like, previously we can have, like, you heard about the emulsion and different names for coatings. Emerging trends is to reduce volatile organic components to become more environmental friendly. So for that, we go for the solid coatings. Solid coating means we reduce amount of solvent, but we increase the spreadability using microfluids and so on. But for us, we just use a single layer coating instead of a multi-layer coating using nano materials incorporation. So maybe you would have seen the advertisements, nano coatings, nano composites.
Oh yeah. Okay. Okay. Thank you, Professor, for your answer.
Okay. Thank you, Diani. So another question, please. Yes. Mick, please.
Okay.
Okay.
Okay. Sorry, Prof. Ramesh, yeah. Prof, when you code your material with, for example, Z and O, yeah, Z and O, yeah, zinc oxide, how do you increase the bondings between Z and O film and the coated material? Did you make, for example, for the heat treatment to diffuse further Z and O into the substrate? That's all.
Okay, actually our coating is polymer binder, like silicone acrylic or acrylic polyester. We disperse the zinc oxide nanoparticles, less than 5% of zinc oxide nanoparticles using sonication method. We use a solvent intercalation method. Solvent intercalation method is we immerse the nanoparticle in solvent. So it will become like once it immerse, it becomes what do you call bigger bulged because it absorbs the solvent. Then that material will be added with this binder solution. We blend it, and then when we apply coating, after that the solvent evaporation, so the nanoparticles will be settled in the layers of these polymers. Then it's called solution intercalation method. So that's what we do this preparation of coatings.
Okay, thank you very much, Prof. Thank you very much.
Okay, thank you. The next question.
Thank you. Professor Kasih, my name is Ronius Marjunus. I'm from University of Lampung, Indonesia. First of all, I would like to send my greeting because I know some colleagues from University Malaya. Perhaps could you send my greeting to Professor Harith, Professor Hasan, and also Dr. Zarina. Thank you.
Oh, they are my colleagues and my teachers.
Okay. Okay, so regarding your presentation, it was very nice presentation. I also have done research together with my colleagues in the Department of Chemistry at the University of Lampung, also to prevent the corrosion. We are using polyphenylpyridine. So my question is, which one is better actually between graphene and polyphenylpyridine? Thank you very much.
Yeah, thank you for the question. I think I understand it's a conducting polymer, right?
Yes. It's kind of polymer.
It's a conducting polymer. Yeah, so conducting polymers, sometimes we use the polyaniline based materials as inhibitor also. So there will be a problem, maybe like when we add the conducting polymer, they may have a network to initiate the corrosion instead of corrosion inhibiting. But if we need a proper surface modification, so it may affect this. Even the same thing will happen to graphene. Graphene, we have to disperse properly. Otherwise, if the graphene make a network, then the conduction will be happen very fast, and corrosion will be faster, initiated and propagated faster. So for both materials, we need to have a proper isolation technique or surface modification technique to avoid this kind of activities.
Okay, thank you, Professor Kasih.
Okay, thank you, Professor Kasih. And the time is up for this session. Thank you again from Professor Kasih. We give applause to Professor Kasih.
Thank you.
Okay, next time you can go to Indonesia. I think not too far.
Sure. I missed this opportunity. Thank you.
Okay. Thank you very much, Professor Kasih. Okay, we go to the next speaker. This is Professor Agus Supriyanto. So please proceed your presentation.
Okay, thank you very much, Prof. Nuriani, as a moderator for the time. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. it's honor for me to have the opportunity to talk about solar energy. With the topic is dye sensitized solar cell in the conference. Okay, this my campus, yes, Universitas Sebelas Maret, UNS, UNS and NUS the same, have the same letter. Yeah. Okay. The student body Universitas Sebelas Maret have around 46,000. Yes. Then UNS have 40 faculty and have a vocational school and postgraduate. And campus area have 65.5 hectare. I think is enough big area, yeah. Okay. This interesting. The based on ranking against, yeah, from Times Higher Education World University ranking, UNS in the world, the ranking position 1,200 until 1,500. Yes, it's different with the news. Yeah. And in the Indonesia, UNS have a ranking position as the 7. According to Webometric ranking, UNS has secure position in the top 10, yeah, best university in Indonesia. Please applause to UNS. Okay, the next, this is my campus located in Central Java. Yeah, if you want to know more information about UNS, please visit to our website UNS ACID. Okay, next. Okay, the faculty mathematics and natural science have equipment facility to characteristic material test to supporting solar cell material research, such as XRD crystallography, yeah, IP meter, Catley instrument for IP curve, then scanning electron microscopy, and IPCA, yeah, incident potent to current efficiency, and have FTR spectroscopy, then also UVB spectroscopy. Okay, next. Based on solar radiation intensity, yeah, that the intensity of solar radiation reaching the Earth is quite extensive and large, especially in the equatorial region. Indonesia is located on the equator region. Okay, the archipelago Indonesia is in like green area, have solar radiation range of 1,300 kilowatt hour per meter square, as enough big radiation intensity. Okay, next. Based on the solar energy potential, that the solar intensity radiation throughout the Indonesia archipelago with an average power up to 4 kilowatt hour per meter square. Yeah. It can be seen the table that solar energy potential for solar cell, solar energy can reach potency have 207 gigawatt is a very big potential, but the utility installation of solar energy only 0.50%. It's very small for utilities in Indonesia. Okay, it's very interesting, yeah, for political will in government. Okay, next. Okay, what is solar cell? A solar cell or photovoltaic cell is a device that can convert sunlight energy into electrical energy. Yeah, solar cell made from silicon have P and N-type junction structure. This is where the mechanism for transporting electron becomes an electric current. Okay, next. Okay, next. Category of solar cell there are two categories. The first an organic solar cell and the second organic solar cell. Of course, the significant role of material science in develop alternative energy source, especially solar energy or solar cell as renewable energy. Okay, next. Okay, solar cell have three generation. The first generation for water base. Second, for example, monocrystalline silicon, polycrystalline silicon, and multi-junction cell. Yeah. And the second generation based thin film, for example, amorphous thin film silicon, cadmium telluride, copper, indium, gallium, selenium, and so on. And the third generation have low cost and high efficiency. Okay, for example, the DSSC, dye-sensitive solar cell, quantum dot sensitive solar cell, organic photovoltaic, and perovskite solar cell. Okay, next. From the best research by the National Renewable Energy Laboratory from the USA, so that the develop of solar cell material, an organic solar cell have higher efficiency performance. Yeah. But organic material still small, around 17%, and dye-sensitive solar cell still 12%. Yeah. Okay, next. The performance of solar cell generation, yeah, for first generation silicon solar cell, based on theoretical, have efficiency 26%, and of course already commercial. But as first generation have expensive, then the silicon fabrication process is very difficult and complex. And the second generation thin film solar cell, based on theoretical, have efficiency to 22% and have high coefficient as solar absorption, then cheaper, yeah, than the first generation. And the fabrication process produced was the pollute the environment. For the third generation, based on the theoretical efficiency, 14 until 20%. The raw material easy to find and easy fabrication process. And so the disadvantage is that is used liquid electrolyte, so it can evaporate. Okay. Next. This is so there are some of the DSSC-based solar cell module that have been made consisting of a small cell. This is a prototype of the dye-sensitive solar cell that our team made for the application of energy source of lower light and like LED. Yeah. Okay, next. The advantage of the ICSAS solar cell: the first, having low fabrication cost. Yeah. The second, have environmentally friendly material. The third, have flexibility, very easy to custom. Yeah. Then the fourth, and also have aesthetic. The color is not monotone. compared by silicon solar cell. Okay, next. Okay. The other disadvantage advantage the SSA have deliver 65 until 300% higher power output on cloudy day, yeah, compared to silicon and thin film solar cell. Yeah. This is the SSA cumulative from morning to evening has accumulated large amount of energy compared to silicon and other unorganic material. Yeah. Okay, next. Okay, the roadmap the SSA module utilization, yeah, ini from reported by ID Text X. Yeah. This roadmap show the development of the SSA solar cell application starting from portable electronic energy source, yeah, such as gadgets, solar window, rooftop, outdoor, and so on. Then the SSA in the market, yeah, from Giselle company. Ini this bag, a mouse, yeah, a keyboard, and so on. Yeah, these are various device product based on the SSA solar cell. Next. Okay, this research contents of publication of the SSA, yeah, have consisting conducting plate, working electroda, dye photosynthesizer, electrolyte, counter electroda. However, everything in one solar cell must have strong seal and of course have its manufacturer. Yeah. Okay, next. Okay. The SSA mechanism, if we think how the SSA work, is really similar to the photosynthesis in plant. Yeah. With is make the sun as the main source. Yeah. The process of photosynthesis takes place in condition where the energy of sunlight is transported into chemical energy. The electrons that are generated are passed on to the acceptor. So the structure of the SSA consisting a glass substrate, transparent conducting, yeah, nanoparticle semiconductor layer, TO2, organic dye, electrolyte, counter electroda, and conductive glass. Okay, next. Okay, this the SSA mechanism. The first, when the working electroda on the SSA is exposed to photon, yeah, the photon energy is absorbed by the dye solution attached to the surface of the TO2 particle. And the second, the electron of the dye molecule will be injected into the conduction band of the TO2 semiconductor, which acceptor. The dye molecule left is in oxidized state. And the third, there is a transfer of electron through the external circuit to the opposite electroda. And the electron mediator carried out by the iodide and triodide, which can generate cell cycle process. And the excited electron will reach in the electrolyte and return to the cell or to the oxidized dye. Okay, next. Okay, dye have the molecular structure of natural dye, can absorb light where the structure similar to structure chlorophyll and phthalocyanin from natural dye. Yeah, we have experiment with binahong leaf, sawi leaf, and so on. Yeah, there are two types of dye, namely natural dye and synthetic dye. Yeah, the one of the natural dye known to have good performance is chlorophyll dye, because chlorophyll is the main pigment that is effective as a photosynthesizer in the photosynthesis process of green plant.
Excuse me, 3 minutes.
Okay.
Professor Gus.
Next, the addition of metal to the sensitive material to improve the SSC performance. Next, this we have this experiment, the absorption characteristic of natural chlorophyll. Yes, this is my experiment still very small. Yeah. Okay, next. This performantable natural dye for the solar cell, ya, start kulit manggis, binahong, until alga, ya, still small, ya, but the addition metal can increase the efficiency of the SSC. Next, okay, this I was experiment natural dye and metal study. Yeah. Next. We also tried to do hybrid of natural dye with synthetic dye, namely dynamo, DNF15. Yeah. So by adding variation of the concentration of dynamo, the performance of the DSSC is still low. Yeah. However, there was an improvement after being given synthetic dye. Okay, next. The study hybrid synthetic dye, yeah, with metal concentration, so that with Ag metal, yeah, can increase quite significantly to 6.29%. Yeah. However, it is again with more concentration, the performance the SSC will decrease. Is interesting that experiment. Okay, next this study synthetic dye. Yeah, I compare to the other study researcher. Yeah, that the SSC performance parameter of synthetic dye, that the synthetic dye, yeah, I have efficiency 4.95%, yeah, is enough excited, yeah, because compare the dye, artificial chlorine type, novel organic dye, yeah, and then new organic dye. Gitu, ya. Okay, next. This I was experiment performance parameter of the SSC, ya, dengan with metal addition, metal photo anode, ya. The also conducted to study of the addition of metal concentration, Ag metal, and this how the affect the performance of the SSC parameter. The addition of metal concentration in the SSC made from synthetic, yeah, DNF was significant enough to obtain an efficiency of 6.29%. Yeah. Okay, next. Okay. What we can improve or modify to get high efficiency? The first high voltage open circuit value have semiconductor with large band gap 3.3.2 electron volt, for example TU2, yeah, semiconductor, and the redox potential of the electrolyte is more positive, and the second high current short circuit value have the visible light absorption area by the dye is wide. Dye regeneration by electrolyte is expeditious, and the good electron conductivity and electrolyte, and the surface area of the semiconductor and the counter electrode is large, and the charge transfer resistance of the counter electrode is small. So the electrocatalytic activity of the counter electrode is good. The third for high fill factor, yeah, have the potential of the counter electrode correspond to the potential of the electrolyte, and the resistivity at the opposite electrode is small until around 3 centimeter. Okay, next. Okay, from the research experiment, we have the study of the ICSAS solar cell material device. Is very open to achieve optimal result ranging from dye optimize, metal doping, electrolyte, counter electrode, and the other. The second, if the achievement of efficiency is close to theoretical at 14 to 20%, then this is certainly quite promising as an alternative innovation from new and renewable energy towards transitional energy to reduce carbon emission and be environmentally friendly. The third, the research community in Indonesia has begun to work on DCC solar cell, but to step into transparent solar cell prototype technology still needs study and application that require standard tests of the characteristic of transparent solar cell. The last, to achieve this a cross-sectoral approach is important in this research. Collaboration with research institution, it is a necessity in building a DCC solar cell prototype technology in transparent form. Yeah. Okay, thank you very much for your attention. I return to moderator. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Okay, we give applause for Professor Agus Supriyanto. Okay, the next is the discussion session. Please, questions from audience. Okay, please from Universitas Lampung. Yes, please.
Thank you, Prof. Nuryani. So thank you, Prof. Supriyanto. It was a very nice presentation. So I have some questions regarding the solar cell or regarding your research. So the first one is, I'm interested, how did you produce the solar cell here at the UNS? I mean, do you have such a equipment, such like MOC video or something like that? So because it's really interested to know about that. And then the second one, as we know, like we have just talked about also another research in physics like a superconductor, because in solar cell it's also like a superconductor. So the point is how to reduce, how to increase the temperature, the critical temperature of a superconductor, and then at the solar cell, the big question is also how to increase the efficiency of the solar cell. So as long as I know that at the moment right now in our world we only can reach until something like 30% the efficiency, right? So my question is there a possibility to simulate or to predict or to simulate the synthesis of the solar cell, firstly by computational methods instead of we are doing experiment again, and then we cannot get the very maximum efficiency. So this was the two questions from me. Thank you.
Okay, two questions, Professor Agus. Okay, please.
Okay, thank you very much. Question from Pak Roni. Yes. Okay, the first, how to produce a solar cell in ONS. Yes. Okay, we have a research group. Group advanced material solar energy, especially organic solar cell, because the fabrication of organic solar cell, especially DSSC, can make easy, yeah, because DSSC solar cell can called kitchen solar cell, yeah. Everywhere can make solar cell based DSSC solar cell. Yes, cooking. It needs experience, yeah, needs experience to how to fabricate solar cell. We have the group organic solar cell, especially the DSSC solar cell, and ya ini ya apa? Ya, more experience, ya, more experience. Yeah, because we have experience. Do natural dye cannot improve, and so I go using synthetic dye from Dynamo, Switzerland. Swedia, sorry. Yeah, Swedia. Can using natural dye, so can addition metal to improve efficiency. Yeah. Please go to slide number 27. Okay. Next 27. Next slide. Yes, okay. Next again. One. Okay. I will experiment the synthetic dye, and so add metal. Yeah, is very significant until 6.29%. Yeah. That the Ag dope, yeah, the Ag metal have the conductive, and so the particle size is small size, yeah. So cause the increase to generate, yeah, non generate is increase to transport electron inject to TO2 semiconductor. Okay, compared to Fe metal, iron metal, yeah. For example, the didation, yeah, have efficiency 1.27%. Then iron metal has a decrease because Fa iron have particle size big size around 1 micron. 1 micron. So that for particles, the big particle size cannot to increase to increase the efficiency lah, yeah, the efficiency of solar cell. But for small particle size metal can improve to efficiency.
Second question. Can simulation increase the efficiency using simulation? That's correct?
Yes. The use for simulation experiment.
With the experiment, it's just simulation.
Yes, we have also experiment, yeah, not using stimulation. Oh,
okay.
Yeah.
There is an experience about using
but
the simulation.
We have the group. We have the analysis have property of metal. They have a particle size from metal to addition to efficiency. Okay.
Okay, thank you, Professor Agus Supriyanto, Professor Ronit. Thank you. The next question. Oh, many questions. Okay. Okay, please. Please make.
Okay.
Name?
Thank you for the opportunity. Okay, my name is Pram. I'm a student of Physics Department of Sebelas Maret University. And my question is, when we add metal, we can increase the SST efficiency. But how can it be? But in fact, in that data, okay, sometimes when we add some metal, let's say Fa in TiO2 exactly, it cannot increase, but exactly decrease the SST efficiency. But my question is, how it can be when we add metal in the SST, how it can increase? And the second question in my second question is, how to choose the best metal for the SST when we combine it, let's say for TiO2 semiconductor? Maybe that's my question. Thank you.
Okay, thank you for the question. Okay, please, Professor Agus.
Okay, thank you very much, Bram, for your question. Okay, of course, the addition other material to the SST may not necessarily lead to increase efficiency, because the performance of the cell depends of several factor, yeah, including the property of material of metal used, yeah, and the overall structure, the SSC, and design of the cell. Yes. Other metal may have similar issue or may not be as effective to generate transport electron, yeah, as silver Ag. For example, particle size TiO2 have around 200 until 300 nanometer, yeah. If at the metal have small particle size, for example, Ag have around 1 nanometer until 100 nanometer, yeah. Of course, this can give the transport electron from die toward TiO2 semiconductor. Yeah. Well, the same goes for Ag particle. Yeah, if too many enter, it will actually to transport electron. I think.
Yeah, okay. Thank you, Professor Agus Supriyanto. Any question, please? Okay, yes, please.
Thank you. My name is Kutirana Kauri. I'm from Professional Teacher Program. I want to ask about why Indonesia have very small implementation of solar cell. We know that from the presentation, Indonesia have high potential to develop PLTS. From the data, we know that Indonesia have high radiation intensity is about 4.8 kWh per day, but the implementation is very low. Thank you.
Okay, thank you very much for the question, Prof. Agus.
Okay, thank you very much for your question. Okay, this depends on political will of government, yeah. Okay, actually Indonesia has made a roadmap, yeah, regarding the develop on instalasi new renewable energy, yeah, based on RUEN, Rencana Umum Energi Nasional, from Dewan Energi Nasional, yeah. For the years by 225 years, yeah, renewable energy must be able to reach until 23%. Yeah. However, the reality is that we are still unable to achieve this target. Yeah. Okay. One of the factor for instalasi solar energy plant is that the operational cost of battery, yeah, as energy storage are still very expensive. Yeah. If compare the price of electricity from solar energy or solar power plant is already around 5 until 7 cent US dollar, yeah, per kilowatt hours, yeah, per kilowatt hours. However, when compared with the power plant from batu bara, yeah, is currently operating as, I think, the price of electricity from this coal power plant is still much cheaper because the production cost only 3 cent US dollar per kWh. So why installation in Indonesia still 0.15%, yeah, because still cheaper to installation solar cell, yeah, in Indonesia. Thanks.
Thank you very much, Professor Agus Supriyanto. We give applause to Professor Agus Supriyanto. Ladies and gentlemen, this is the end of the keynote session from Professor Kasi and from Professor Agus Supriyanto. And then we give to MC again. Thank you.
Ladies and gentlemen, thank you so much for Professor Nuriani for being the moderator as the second plenary today. And also thank you so much for Professor Muhammad Aziz and also Professor Agus Supriyanto have delivered their great speech in the second session of the plenary lectures today.
Ladies and gentlemen, we are now at the end of the plenary lecture session. The next schedule will be a lunch break.
Also, but before that, I would like to inform you about the parallel sessions today. The parallel session will be started at 1 p.m. here, and the closing ceremony will be held in each parallel of each room.
Once again, please everyone to give a big round of applause to our wonderful speakers. And we want to say special thank you to BRI as partial support for this event.
On behalf of the organizing committees today, we are saying thank you also for your stay here to join this conference today. It was really an honor to us to have you all here. And see you in the International Conference on Science and Applied Science 2025. Wassalamualaikum warahmatullahi wabarakatuh.
Invincible.